Fractal Minds and the Sacred Cosmology, and it's all about brains, behaviour, mind and psychology. Now, this talk continues from the first talk called 2012 and the Fractal Brain Theory, whereas that was more about kind of neural substrates and neuroscience and brains. This is more about mind, psychology, our introspective realities and the kind of cognitive aspects of our life. So it's really more to do with the kind of higher mental aspects. Now, this talk is standalone, so I'll recap necessary points from the first talk as I go along. And the two talks kind of complement one another. And there's many copies of the first talk on the internet called 2012 and the Fractal Brain Theory. Okay, so just to cut out the preamble, we'll go straight to it. The basic idea is that the brain is stupendously, fantastically complex in structure and also process, but what we'll show is basically in structure, it's actually really simple in structure. And also what we'll show in particular in this talk, the process is also really, really simple. And the reason is because the brain has a fractal structure and also the process of the brain is recursive. Okay, so new words there. So we're going to explain first what recursive means and what fractal means, just kind of preliminaries, just to set up the kind of rest of the talk. So just skimming stone over material, some from the last talk, and also introduce this idea of recursivity and recursive process. Now, the basic idea, okay, in a nutshell, is fractals. Now, if you see this diagram here, Russian dolls, basically that's essentially fractal. So even though it looks really complex, it's really your normal Russian doll, but in a kind of modified form. So you've got one basic Russian doll, and it's basically nested within itself. So what we're doing here is we're basically taking a basic shape, and we're transforming that shape, in this case making it smaller, and then we're putting that same shape within itself, and we're doing it again and again. So this shape here, you can see it's fractal, because you're doing it again and again. So that's called self-similarity. The shapes inside this little mini brain look like the overall shape, and same with these Russian dolls. It's actually the same doll but replicated at all scales, all over the place. So that's what fractal means. And that's a very simple mathematical fractal called a Sierpinski's triangle, a very old one. And that's a very more complex dodecahedron fractal. That's the kind of classic fractal of fractals. That's called a Mandelbrot set. And that's a fractal because you have this kind of basic snowman shape, but basically, the Mandelbrot set contains an infinity of those snowmans. It's been mathematically proven. So there's an infinity. You can see another snowman there, and kind of snowman kind of sticking out. So that's a fractal. That's the kind of granddaddy of all fractals, you might say. Now, recursive process. What does that mean? Okay, recursive process. Now, recursive process and fractal structure really goes hand in hand. So if we have fractal structure, then we have recursive process. Now, one example will illustrate what recursive process means. And this is, in a tennis match, you know there's a final, then there's a semi-finals, and there's quarterfinals. Even though these are separate tennis matches, all these separate matches kind of funnel into the finals. So basically, they're playing matches here, and then recursively, the quarterfinals lead to the semi-finals, then recursively, that leads to the final. Now, you can imagine in your minds, everyone in the world is a tennis fanatic. So you have a huge hierarchy of all the people in the world, and they all play tennis in this kind of like recursive, convergent hierarchy, and the winner gets to be the king of the world or queen of the world. So I know probably most of you don't imagine those kind of things, but there are people in this world that do imagine those kind of things, and actually kind of vying to actually become this tennis star of the world. It's called the pyramid of power that some people have played this game. We'll talk about this more later in the talk, but anyway, digressing slightly. Another example of recursive process is fertilized egg becomes 2, becomes 4, becomes 8, becomes 16. So that's a divergent recursive process. So you get the picture. Even though we have this kind of like a tree structure, the process is actually the same structure and same process repeated throughout. The idea is that the brain is fractal and that the process of the brain is recursive. And it's actually a very simple recursion underlying all the processes of our minds, all our behaviour, and all psychology, which I'll show in the second half of the talk. Just a skimming stone preliminary. I talk about the brain and mind. Just give a skimming stone overview of what the brain looks like and what it kind of basically, the structure and what it kind of basically does overall and its overall fractal structure. That's your kind of classic view of a brain, a sideward view, and it's very convoluted and curvy, but it's most of the brain is what's called cerebral cortex, and that's what you see. Now, that's basically a huge sheet about that big, folded up. That's drawn to scale, can you see? That's the side of your head. Now, if you take that kind of huge sheet and you scrunch it up, that's most of your brain. So 80% of your brain is cerebral cortex. If you strip out all the wires, you can actually flatten out into a flat sheet. Now, this flat sheet, one on each side of your head, is made up of these columns, and each column is about 3 millimeters wide. And this is the basic building block of your cerebral cortex. And there's millions of these columns in your cerebral cortex. Now, the basic building block, the column, is the same in a mouse brain. And it's actually the same design, same diameter, same number of neurons, and the same architecture as in a mouse brain as in a human brain. So essentially, the same building block is actually makes up most of your brain. And so this flat sheet is demarcated into, before they divided into 50 regions. Now they're divided into about 500 separate regions. So like a patchwork quilt, it's about 500 regions. And these regions do separate things. So that all handles vision, and that handles touch, that handles thinking, motor control. So this flat sheet, very thin, about a few millimeters thick, that's where most of the action's going on, plus all the wiring that links it up. Now the wiring is really intricate. What I have to also say is basically these patchwork quilts, flat sheet little patches of cortex, they work topographically, which means they actually process like pictures. So if the monkey sees that pattern, then that pattern will be actually on its visual cortex. And same with sound, and the same with a touch. And so it's basically like you're processing with images. It's a flat sheet, and it's actually literally processing topographic maps. That's interesting, isn't it? And okay, so these patches, that's all your visual areas. They're kind of really intricately linked up, but they're all linked up in these kind of hierarchies. And all these hierarchies funnel into a part of the brain called the hippocampus. So there's an equivalent hierarchy for touch, for hearing, etc. And also hierarchies that go the other way, that like diverge outwards. These hierarchies are to do with action. And then so this patchwork quilt is really intricately linked up in this way. And all your senses funnel into the hippocampus, and then all your doing hierarchies that project outwards come out of a part of the brain called the cingulate cortex. Okay, so that's the basic design of your brain. You've got overall design. Now it's fractal because the columns we talked about just now, the columns that are found in mouse brains and human brains, it's a basic design. So the column will project to other columns, these arrows projecting to other columns, and to columns on the other side of the brain or to completely different areas. And then would also take inputs from other columns, from neighboring columns or columns in very distant parts of the brain. And fractally, the columns are made up of these pyramidal neurons in the same design, projecting out from the neuron, projecting in from the neuron, but also just kind of looping back to the vicinity of the cell body, and also in the column, looping back. And fractally, the columns are arranged into macrocolumns in the same arrangement, kind of projecting out to neighboring macrocolumns and looping back on itself and projecting in. And then these patchwork quilt areas will take from neighboring patches, project it out neighboring patches, and then again loop back on itself. So neurons contained in columns contained in macrocolumns, and macrocolumns making up patches. So it's kind of contained within another. Now, if we go back to those hierarchies we talked about, there's another way in which the brain is a nested Russian doll structure, and that's because that's another example of a loop involving the striatum, and we'll talk about it a lot more in a minute, because it's a very important auxiliary part of the brain. Now, so that's the entire brain, all the kind of sensory hierarchies funneling into the hippocampus. These are your emotion centers, and that's all your kind of motor hierarchies and cognitive hierarchies funneling out from your cingulate cortex. The same thing, you're basically kind of like roots of a tree funneling into the hippocampus and the branches of a tree projecting out. And that's your entire brain. But then the entire cingulate cortex will project a thick bundle of fibers back to the hippocampus. So you see kind of like projecting in like the roots of a tree projecting out, then it's kind of looping back. But it's happening at all scales. So these are patches of cortex, have that same projecting in, projecting out, looping back structure to macrocolumns, to columns, to neurons. So Russian dolls contained within Russian dolls, contained within Russian dolls. And if we look at these hierarchies, now, even though it's connected as a hierarchy, side by side, like patchwork quilts, patches side by side, a way of visualizing this as a Russian doll structure is to kind of use the analogy of computer directories, because you know that you can specify directories with a list of names, but that list of names also specifies a nested folder structure. So simply by the same principle, these hierarchies are also Russian doll nested, but laterally nested, whereas within the patch, neurons are physically nested within the column, physically nested within the macrocolumn, physically nested within the patch. So the entire brain reduces to one great big Russian doll. So that's the basic idea, that the entire brain is arranged in this kind of Russian doll structure, but also processed, the kind of component processes of the brain is also fractal. So at all levels of your brain, like neurons compete with one another, synapses compete, neurotransmitters compete to bind onto receptors, columns compete with one another, the winner suppresses its neighbours, and you know your perceptions compete, and you also know when you make a decision, that's like a competition, isn't it? Or your moods compete, so is the glass half empty, is it half full? And also neurons, synapses link up, and also dendrites link up on the cell body, and then neurons link up, and you know that patches link up, as I've just shown, and also ideas link up, chain up in space, but also link up in time. So the process of the brain is completely fractal. And I'll show later on that these microscopic atomic processes are fractal, but also recursively nested, so making one overall process that covers all these fractal processes. That's the key idea of recursion. Now, even though the brain is squishy, squashy, and messy, and you know, kind of Jedi-like, and there's a kind of way of looking at the brain which is actually really ordered and really kind of quite mathematical, which we'll discuss in a second. Now, two auxiliary structures. Okay, so most of your brain is this kind of flat sheet patchwork quilt of all these different functional areas. Now there's two structures of the brain which form additional loops with this patchwork quilt cerebral cortex, and they are called the striatum and the cerebellum. So it's kind of two auxiliary structures. That's the striatum, which we covered a lot in the first talk, and this is the cerebellum, which is back here. So the cortex is most of your brain, but these are two very, very important auxiliary structures, striatum and cerebellum. And we can explain these two structures by really examining the parallels between the two structures, and there are many parallels, but there's also a complementary, which actually is a clue to why we have this differentiation between these two structures. Now, the parallels is that both of them form closed loops with patches of cerebral cortex, particularly in your frontal lobes, to do with thinking, doing, and action. And they form these closed loops. So they don't do anything on their own. They basically form loops with the cerebral cortex. So they work with the cerebral cortex to form these loops, coursing via the thalamus, which is like a relay station. And another parallel is that they're both involved in procedural memories and skills, automatizing sequences in time. So if you learn a skill, playing a musical instrument over time, or learn a recipe, a sequence of patterns of doing things over time, you're going to be using your cerebral cortex working with your striatum and with your cerebellum. So that's another parallel. Another parallel is that for years, for decades, scientists thought that the cerebellum and the striatum were to do with motor control, and they thought that's all it was to do with. So they thought it was connected with the premotor cortex and the motor cortex. So they thought it was to do with movement. But over the past few decades, we know now that the cerebellum and the striatum is involved throughout your frontal hierarchy. So it's also to do with cognition, thinking. And it's also to do with spatial reasoning. And it's also, both these structures, also recently, we now know for sure that both these structures are heavily involved with emotional processing as well. So an entire hierarchy of your prefrontal lobes and prefrontal cortex, these structures work throughout to form these kind of loops. And there's other parallels as well, but the clue as what they're doing and how they're doing it comes when we look at where they are different, because they're different in this way. This looks like it's just a bit of background. I mean, that's the cerebellum, and again, it's like a flat sheet. So it's like a flat sheet. It's wrinkly, but that's a kind of cross section. You see, it's like fractally folded. That little part of your brain, if you scrape out all the wires, and you can flatten it out to a kind of flat sheet, and that flat sheet is actually about 60 centimeters. and about that wide. So that's kind of compressed. You see it's compressed, fractally compressed, and it's all squeezed into your back of your brain there. Another thing about the cerebellum and the striatum is topographic maps. So you can see this is a topographic map of toes, hands, and head. And so in the same way that the cerebral cortex has topographic maps, the striatum and also the cerebellum, again, topographic maps. And you have a topographic map there for the frontal lobes and the cognitive divisions, and the central divisions deal with emotions. So again, it's kind of a pictorial topographic processing in the brain. Now, where these two structures are different, okay, is a clue to what they're doing, because what they're essentially doing is they're automatizing behavior. So what they're doing is basically making behaviors, thoughts, and emotions automatic. So this is really important because most of our behavior is automatized, and it's basically, the skills and procedures are basically something we don't want to think about, we just want to do it. And one of the clues as to how they're doing it is the projection pattern. And this is quite recent research. Is that, okay, the cerebral cortex, recapping some stuff from last talk, is divided into 6 layers. And if you go from the emotion centers down to the kind of motor atoms of actually moving your arms and legs about, that is a hierarchy. So if the top is your emotion centers, and then second is your cognitive division, and then the cognitive division sends commands down to your kind of motor cortex, then that's kind of top down, you see. Now, the top down pattern of projection from your emotion centers, prefrontal cortex, cognitive centers to your kind of primary motor areas projects from layer 5 down to layer 1. But vice versa, when you go from your sensory areas and feeding back from, when you make a movement back, the bottom up pattern is actually from into layer 4. Now, interestingly, the striatum comes back from its closed loop with the thalamus. Okay, basal ganglia and striatum are interchangeable terms. Will project into layer 1, top down. But the cerebellum will go via the thalamus and project bottom up, layer 4. You see, this is a clue. So there are parallels, but this is where they're complementary, you see. Now, suppose when you learn to drive, you change your gear. American audiences probably go, what the hell is he thinking about? But basically, in Europe, we have to change gears in cars. So we have to visualize the kind of gear pattern, and then we have to visualize it. And when we first learn how to drive, we kind of go, and you look down, and driving instructor says, don't look down, you mustn't look down because you're going to crash. And so you have to visualize, and you have to move it like that, and you think you have to move it like that. Okay, and then it's a top-down command, move it over there, move it over there. But it's kind of bottom-back feedback. You feel the sensation of your hands moving, and the feel of the gear stick, and that's bottom up. Now, what if over time the patch of motor cortex is able to learn the top-down signal and also learn the bottom-up signal? So basically, you just issue the initial command, move from gear 1 to 5, straight to 5, I'm in a hurry, and basically it just does it, you see. But you see what it's doing? Basically, it's actually modeling the top-down command via the thalamic closed loop, but it's also modeling the bottom-up command. So it doesn't need to receive instructions from bottom up or top down anymore. Just say, do it, and then off it goes, it does it. So imagine this kind of facility happening throughout your prefrontal cortex. And that's really useful, isn't it? So basically most of your brain, most behavior is involving the striatum and the cerebral cortex. So it's really, really important. And most of your behavior, what we do, happens over time. So these two structures are really, really important. The other major difference we discussed in the last talk is that the basal ganglia and the striatum is modulated heavily by dopamine, which is the kind of chemical of addiction and motivation. So that's another difference. So that's our basic kind of design of the brain, basic layout of what the brain is and what it's doing. Now the brain, there's a way of looking at the brain, which I think it's a revolution in way of in looking at it. And it's a way of looking at the brain that sees the brain as something that's really discrete, quantized, gritty, and digital, and also grid-like and square and binary. Now that sounds very unfamiliar because we think of the brain as something quite messy and quite disorderly. But recent research has shown that basically there really is this kind of very neat mathematical order to the brain. And we can capture this order using binary trees, which is one of the most fundamental, is the most fundamental data structure in all computer science. So it's a very fundamental idea. And it seems far removed from real brains, this kind of quantized, gritty, kind of a square binary tree way of looking at things. Now, okay, if that's a binary tree, and that's a binary tree, you see, that's also a binary tree. And I can use binary trees to make grids. So I'm making like topographic maps with binary trees. And then I can make an even bigger grid. And then I can, and so on. So that's still a binary tree, isn't it? Can you see that's a binary tree? And that's also a binary tree. And that's also a bigger grid. So in a sense, I'm modeling these flat maps, and your brain is flat maps. So I'm kind of like using binary trees to model flat maps. Now, when we realized that brains come to being through cell division, that fertilized egg becomes, becomes kind of 2 cells, then becomes 4 cells, then 8 cells. But that's how your brain comes into being. So inherent in the way bodies and brains come to being is this binary pattern. We showed in the last talk, okay, so that's a binary tree. Can you see, it's flat, but it's drawn in such a way that basically that's the main branch. It's branching into 2, branching into 4, etc. So that's a binary tree. We showed in the last talk, I mean, we won't go through it again, that basically you can use this kind of like cell divisioning process and lineage to mark out brain regions. You can mark out regions using lineage. You can't mark out every single neuron and how every single neuron will connect, but you can basically map out the basic regions of the brain and give them a binary code. And then you can, using RNA, you can give them tags. So you can use binary trees and binary codes to specify addresses within the brain, the overall structures of the brain, which then allow you to very precisely wire up the brain, okay, and define it digitally. So here's a kind of cerebral cortex, and that's the hypothalamus. This is kind of like a digitized brain, which corresponds to those areas. So basically, you're basically digitizing all these separate areas. And because it's fractal, and you can then go on to subdivide. Now this is a recent finding that even though this gritty way of looking at the brain seems far removed from real brains, what they found is that the actual wiring of the flat sheet cerebral cortex is literally gritty. All the wires only go orthogonally, they only go up or across, they never go diagonal. This is a very recent finding, actually just published this year, March this year. And so in how brains come to being, binary divisioning and also the wiring underneath the cerebral cortex is actually gritty. And also the patches, the orthogonal arrangement of these kind of gritty squares, there's meaning behind orthogonality. So if you go across and down, there's kind of like you're going up hierarchies. So literally underneath the kind of superficial messiness of the brain, there is a kind of orthogonal grid-like binary arrangement. Now, with our digitized brain, if these are overall regions of the brain, these are regions of your hypothalamus digitized. Because it's a fractal language, okay, that's a region, I can basically, using binary trees, I can address different regions by doing a tree walk. But because it's fractal, can you see, basically these are sub-regions within the region, and so on, until you get to individual neurons. So basically, I've kind of transferred from messy brains into a kind of digital language. So I'm doing everything in this digital language now. And it gives, for the same reason why the transfer from analog music, etc., there's advantages to being digital. And the same applies for digital signal processing and technology and for hi-fis. And the same advantages also apply to brains. We won't go into those because that's a little more specialized. This program here is basically just a way of showing that this is me talking, this is sound in the room. And you can see that superimposed is kind of like that binary grid tree structure on top of it. So in the same way I can represent brain regions, I can also represent topographic maps. So if I draw some squares over that thing, okay, so what I've done is I've digitized it, can you see? So basically that's what I just take out the tree now. Basically it's very low res, isn't it? It's not very impressive, but it's just a way of showing that the topographic maps in your kind of in your real brain I've kind of modeled using this digital language. So that's just kind of sound spectra, and then a kind of webcam input. So it's just me digitized, you see. So with this digital language, I can specify the entire brain. I can specify subregions, but I can also specify these topographic maps digitized. Okay, so now we're going to extend our digitized brain and give it really the ability to process space and time and reality, and show some pretty amazing tricks later on that really differentiate human intelligence from animal intelligence in the last part of this first section. So now, so we've got a digitized brain, we've got topographic maps, okay? Now, these topographic maps are quite static, and that's actually comparable to the topographic map of your retina. It's actually quite low resolution. And the reason why you're able to see such detail with your eyes It's because your eyes move around. Now imagine, imagine if I hold my head perfectly still and I look straight ahead and I'm not moving my eyes. So my topographic map of my retina is basically seeing something. That's basically very low resolution. Now, but what I do is I scan around and I hold my head still, but I'm scanning around the room and I can actually focus on things that has interesting detail. So here, that's actual eye scans of the scene and these actual eye scans, depending on what the person's looking at. And but I can move my eyes around, but I can also move my head around now. Okay, I can move my head around. Okay, but I can also move my body around. Now that's moving my retina around, and that's what's giving me what's called egocentric map of the room. So from where I'm standing, the light is over there. That's an egocentric map, and the window's over there. And this egocentric map, we know it's binary because we know of Hemming neglect. We can lose half that world, and it keeps half binary subdivisioning. So in here, the person's got Hemming neglect. It's basically he can see the entire thing, and he's asked to look for the T. There's a T, but he can't. His eyes can't go to the left-hand side. He's lost half his world. If you show him that half, he'll basically subdivide again and subdivide again. So, but literally, there's a binary subdivisioning process going on to our egocentric map. And asked to draw this house, he only draws half of it. Asked to bisect the line, he doesn't do it in half, he does it here. If you give him half the line, he'll go there again. So it's funny, isn't it? It's basically halving his world. So in our egocentric map, we have this kind of binary order. And it's not just, if you're walking down the street, he's lost half the street. So it's fractal. So basically, big things, small things, loses half a world, loses half a plate of food, etc. What it means is that this egocentric map we can represent using binary trees. And sometimes we know how things work when things go wrong. So it's when things go wrong, we see that there is a binary structure to our egocentric map, okay, and our eye scanning map. Now, there's another kind of map called allocentric map. Okay, allocentric means our map of the world with respect to reality now. So it's not egocentric. Now, so I'm standing in this part of the room, and I'm standing in this room in this building. Now, if I move over here, I've changed my allocentric position, you see. Now, this is my egocentric position. It's basically the piano's over there, the kitchen's over there. So that's egocentric, I say. And allocentric means that you have things called place cells. You know where you are in the world physically, X, Y, etc. You know you're in a room, you know where in that room you are. And also we have the ability to what's called dead reckoning. It's sort of Old English called deduce reckoning, which means in olden times a ship, we didn't have a kind of complex GPS, and basically a ship would be in a certain direction and it would go a certain knots for a certain amount of time, and then it would shift to another direction, and then etc. And you deduce where you are from that kind of that information. Now ants and bees can do this really well. So that's actually a physical trace of an ant from the nest. It goes wander, wander, wander. Where's the food? Where's the food? I can sort of the food is nearby. Finds the food and makes the ant line back to the nest. And of course, a bee makes a beeline back to the hive when it finds nectar. So this deduce reckoning we do as well. Maybe not as precise as a bee or an ant, and it's very ancient. The main point here, okay, hexagonals is what this deduce reckoning is represented in our brains, but you can easily represent diagonals and hexagonals as a gritty square pattern. But the main thing is allocentric references, because it's XY Euclidean space, is basically gritty. So we can represent allocentric space in binary language again, binary gritty language. And then we can then represent ourselves in allocentric space with egocentric space within. The main point is that it's a hierarchy. So basically, my topographic map of my retina can actually identify an object, but I can place that object in an egocentric map of where it is in relation to me. But then the egocentric map is in my allocentric map. So it's like a hierarchy. So and because this hierarchy projects the different parts of the brain. Okay, the object recognitions to the perivrinal cortex, and then kind of deduce reckoning place cells as parahippocampal cortex, and then your kind of egocentric map is wired to this other part called a pre and parasubiculum. What we're doing is basically we can take these hierarchies and we can nest them into one another. So the hierarchy of representing something I see exists in the hierarchy of representing where it is in relation to me, but that exists within a binary hierarchy of representing where I am in the room and which room I'm in, etc. Do you get it? So it's basically one continuum, one fractal continuum representing objects in relation to myself, in relation to where I'm in the room. And also, when we reach for something, we're also using the egocentric map. And if I hear a sound over there, then I orientate myself to it. Again, the audio locationing and also my reaching and pointing to things in reality is actually mapped onto that visual, gritty, egocentric map. So we have a way now of representing space. We can represent reality now. My view of reality and me scanning around reality. Now we're going to introduce time. We're going to basically add time to our digitized brain and to our understanding of the world and the brain. That's just a diagram of the hippocampus. Now, these binary trees, if that represents a topographic map, kind of something you're seeing with retina. Now, this binary tree here is slightly different because that's representing time. So see here, we're actually representing a sequence of frames over time now. The idea is that you can also use binary trees to represent time. And we know, even though time seems a continuous flow, we know that time is quantized because of brainwaves. And brainwaves also happen to be in powers of 2, which suggests binary trees again. So because they go up in octaves, these brainwaves, I mean, gamma waves, twice the frequency of beta waves, twice of alpha waves to theta. I mean, people weren't even thinking in powers of 2 when they gave these brain waves names. They just basically measured the power spectra. It just happened to be powers of 2, and this, I believe, supports the binary theory. Now, we know that time is kind of quantized and sliced into little segments because of, say, gamma waves. Your eyes will work with a kind of underlying gamma wave component. Now, if you cleverly give someone something to see, but if you kind of measure their gamma wave, now if you, using computers, you present the image only at the trough of a gamma wave, okay, then the person won't see it. Now if you shift the image, so the image only appears at the peak of the gamma wave, then the person will see it. So you see, like time is literally chopped up in these little segments. And also, because of this looping back structure, what the looping back structure throughout the brain, fractal brain, stratum, cerebellum, all throughout the brain, what it's really allowing us to do is represent time. Because when we loop back on ourselves, we really represent what's happening previously in the last time interval. So we can basically represent 2 time intervals using binary trees and recursively represent hierarchies of time using binary trees. Okay, just to show that these loops are to do with representing time, and it's something fundamental to how we work. And also in music, there's a kind of binary bifurcating and also kind of a doubling structure to music. So notes are arranged in a certain way. In common time music, common time classical music, folk music, rock music, also nursery rhymes, there's a certain meter and structure to music and to nursery rhymes, and it's the powers of 2. Kind of doubling, so notes are grouped in kind of measures of 4, then these measures of 4 grouped into 8, and then 16, and then 32, and 64. If it isn't grouped in that way, then it kind of sounds odd. Okay, so it basically makes nursery rhymes and certain kinds of music easy to register. And also in language, Noam Chomsky decomposes all language, again, in terms of binary trees. So basically binary trees and time is something really that's found in the brain, actually. We're using this to explain how the brain represents time. And it's very convenient that it's also how the brain represents space. On the very top level of our minds, there's what neuroscientists call prospective memory and retrospective memory. Now, it sounds contradictory because prospective memory, this term from psychology and neuroscience, means memory of the future. It sounds kind of contradictory because we normally think of memories as being something that happened in the past. But it kind of makes sense when we realize that we can have an expectation of the future, kind of an idea of what the future is going to be, then we can store that as a memory. So therefore, that's called prospective memory. It's actually a memory of the future. Now, we know that prospective memory becomes retrospective because what's in the future becomes the past. But vice versa, what's happened in the past, we project into the future. That's happened in the past, and I expect that to happen in the future, you see. There was some excitement a few years ago when they found that the structures dealing with prospective and retrospective memory are actually identical, the hippocampus and medial temporal lobes. And that's kind of obvious now when we realize that the past and future are interchangeable. But when we also realize that space and time, because we're representing it using binary trees, we also interchange space and time, because we break spatial things down in time, i.e. a complex spatial image will scan and break down in time. But vice versa, the idea that a composer sees the entire symphony, that we also the notes to this talk, I can see it in my head. That's why I can go on. I can see the notes in my head. I'm spatialized language. So things that we process in time, we also see in space, and also number. We use the same spatial reasoning parts of the brain to process number as well. Now this is really important, because when we take it both together, representation of space and time, you can see it's completely fractal. So representing objects in a pixel in a topographic map with binary trees, within egocentric frame of reference, within allocentric reference, completely fractal, binary trees. And also time, completely fractal, from my prospective memory to my retrospective, right down to my automic representation of time. Completely fractal representing of space and time, and interchangeable. And this becomes really important and handy when we come to create artificial intelligence. Okay. Now, some people are really turned off when we say the word artificial intelligence and reductionism, because it kind of implies that we're machines. But in the second half of the talk, we will go into kind of metaphysical things and show that we'll revisit the idea that that somehow consciousness is God idea later on in the talk. Okay, so just to so people don't get too disturbed by things like expressions like reverse engineering the brain and artificial intelligence. Okay, so okay, we'll reassure people. Because I've known people to walk out the room in disgust in the past, so that's the reason why I said that. Okay, so space and time. Now language, how do we represent things in the brain? So we've got space and time. Now how do we represent things? How does language work? How do we symbolize? How do we represent things? Now we can represent space and time. Okay, this is probably the heaviest part of the talk. Okay, it's to do with coding. We code the space and time in what's called combinatorial codes. Now it sounds really heavy until you realize that when we use numbers, numerals, that's a combinatorial code. When we string letters of the alphabet into words, that's a combinatorial code, you see. You're using combinations of letters to represent words that represent meaning. Now, because it's a binary theory, and it's a kind of gritty binary bifurcating theory, what we use is binary codes and binary combinatorial codes. So just a quick, this is probably the heaviest part of the talk, but it's well worth it to follow this. Now, if I can explain to you what spatial code means, okay? Spatial code means that, okay, suppose that's a neurogenesis neuron dividing to 2, dividing to 4, and I've got 4 neurons. Now, a spatial code is if I say that neuron represents, 4 members of the Beatles, that represents John Lennon, Paul McCartney, Ringo, George Harrison. Not necessarily in that order. I mean, they're all important. They're all great guys. But that's a spatial code. So each one of those, virtual neurons represents one of the Beatles. And you can take this idea to infinity. So it keeps dividing into, dividing. If I branched 16 times, then I'll basically have 64,000 of these, spatial codes. I can represent, rock bands with 64,000 members, say. not that you'd want to form a rock band that big. But now combinatorial codes get big very fast. So if I go to 64 now instead of 16, then I've got a number bigger than the number of atoms in the universe. So spatial codes are handy, they're simple to understand, but they're limited. Now what we can do is basically we can use this spatial coding, we can turn it into a combinatorial code. And how we do it is this. Now I'm still working with 4 neurons, but each of these neurons I can label 0 or 1. So this is a combinatorial code. So I've got 4 neurons. Now in here I can put 0 or 1, and then in the second neuron I can also put 0 or 1. Can you see, as I go across, these are all the combinations of 0 and 1 I can put in those 4 boxes. So with a combinatorial code I can represent 16 things. And I can do the same thing with time. Now, okay, it's almost the same diagram, but it's just past and future. All I'm doing here now is it's actually 1 neuron, but I'm taking that 1 neuron and I'm evolving it in time. So in time t, I'm saying that's 0 or 1, and t plus 1, that's 0 or 1, t plus 2, 0 or 1, t plus 3, 0 or 1. Can you see, going across again, over 4 time intervals, I can represent 16 things again. Now, if you go to mix spatial combinatorial coding and temporal combinatorial coding, then if I go back to my 4 neurons, okay, if I give that a spatial combinatorial code, but now if I do these time loops, if I loop back in time, but I'm looping back not with a single neuron, but actually loop back with the entire combinatorial code, okay, then what it means, I can then represent over 4 time intervals, I can represent 16 times 16 times 16 by 16, which is 64,000. So you can see with just 4 neurons using spatial combinatorial codes and also kind of temporal combinatorial codes, with just 4 neurons I can represent 64,000 things. The only catch is I can't represent these 64,000 things at once, and I can only represent these 64,000 things over 4 time intervals. Now if I take this basic idea and I take it to millions of neurons or millions of cortical columns, and I take it to cortical patches, then I take it to striatal cerebellar loops, then you can see the complexity of things I can represent with my brain. But basically what I'm dealing with is combinatorial codes. Now the space of things I can represent is huge, and we're going to examine this later. How do we represent the things we want to, in our limited space? Now once we have these combinatorial codes, we can give them labels, we can symbolize them or tokenize them. So here's that 16 grid. I can call that I, okay, but I can also break it down recursively. So I can actually give names to these 2 by 2 grids. And then I can link up not these individual squares, but I can link up the actual sub-symbols, you see. So I'm giving them tokens, I'm labeling them now. I'm labeling, these are all combinatorial codes, I'm giving them names. Now it's recursive. Now I keep doing this process further. Now this might represent bar detectors in my visual cortex. So I've given each bar detector a name in a certain part of my visual cortex, at a certain orientation. Then I can use these symbols to represent simple shapes. But you get the idea, and then I can take that simple shape, I can animate it in time. But you get the basic idea, I can basically composite visual things and make complex visual things, and then kind of animate complex visual things in time. But I can also link up simple autonomic muscle movements. I can link them up into complex muscle movements, into whole behaviours. They can chain whole behaviours and link them up together. But what I'm doing is I'm recursively symbolising at all levels of this hierarchy. You see what I'm doing? I'm tokenising and symbolising. Now we get to a level of this process of tokenising and symbolising, which is special because it comes to a level where I can actually say the token. So we have this kind of language loop. It gets to a level, this is the language loop of our brains, Broca's area and Wernicke's area. This actually moves my mouth to say words, and that actually is to do with hearing words and actually registering it as a symbol. So I've taken this process of symbolizing autonomic motor atoms and given them tokens, but here I'm basically got to a stage where these tokens are actually words I can say and hear. But can you see it's fractal, because with words I then form these words into binary trees again, and I form these words into sentences. The important point is basically doing the same fractal compositing process, and then these letters are combinatorial codes and these words are combinatorial codes, but it's on a higher level now. At all levels of this fractal linguistic symbolic hierarchy, you can do 2 things. Once you have a symbol, what you can do is you can recognize a combinatorial pattern and register these symbols up to words. And vice versa, once you have a word, once you have a symbol, you can actually also reconstruct the pattern. So I can see a cat, and then the word cat appears in my mind. Then I can hear the word cat, and I can draw a picture of a cat or visualize it in my mind. So I'm reconstructing and I'm recognizing. You see, it's this 2-way process of taking something complex, spatial, temporal, and converting it into a token or word and stringing it into a sentence. And vice versa, I can hear a word or a token, I can reconstruct a kind of spatial, temporal pattern. Now, when we write in our diaries, we're basically taking an entire day's events and we basically string it into words, kind of like a small kind of facsimile of the day's events. And when we read a novel, we're doing something opposite, basically taking those words and we're reconstructing something in our minds. So there's something really fundamental to what we do. Now, words is really important because this speech hierarchy, this speech loop really spreads to your entire brain. So words and language is really important because we can symbolize our entire brains. This kind of diagram shows from monkeys to chimpanzees to human beings. We see this language loop spreading out in terms of its kind of tendrils, its tentacles, reaching out to the rest of the brain. But really, this is our digitized brain. Really, this language loop really goes to our entire brains. Anything we feel, see, touch, our spatial reasoning, we can actually articulate all this. We can say it in words. And I'll show in a minute why this is really, really powerful. So this is the language loop. So this is, if you think of a color-related word, that part of your brain will light up. You should think of shapes, then the shape processing part will light up. And faces, if you think of a face, then you will, the face-related part, arm-related, etc. Basically, if you move your arm, then you can actually say that in a word. If someone told me to move my arm, then I take that word and move my arm. So you get the picture. It's actually something we do fundamentally. Now, neuroscientists say that we spend most of our time talking to ourselves. They know it from brain scans. I know I do. I know I talk to myself all the time. I mostly agree with myself, but sometimes you get into these horrible, dark rumination phases, don't you? We get, Now, the idea is that if you're going to spend most of your life talking to yourself, which neuroscientists say we do, the idea is to have a productive dialogue. So if you spend your entire life saying, I'm useless, I'm crummy, I was born to lose, then you probably will lose in life. But if the idea of NLP and positive thinking, now this is me switching a gear to self-help guru now. So if you change your thoughts, you can change your life. And if you transform what you think, you can transform who you are. So basically, the idea that words are really important and our introspective reality is essentially made up of language. And language is really important because basically language is going into our entire brains, and vice versa. All the things we feel and think in our brains is going to language. So language is something really fundamental. And also because we're social beings, language allows us to communicate what's in our heads to other people. So language. Now the important thing here, can you see that language is completely fractal? From sensory atoms to motor atoms, right up to language, right up to sentences and sentences and paragraphs and books. Can you see it's a completely fractal structure? And the same process of recognizing and reconstructing is, again, completely fractal. So that's the important point there to remember. Now, just the last section of this, the first part of the talk, is we'll examine the part of the brain now which is really, really important. It's really fantastically important. It's called the polar frontal cortex, or Brodmann area 10. And it's probably the part of the brain which really gives us human intelligence. Now, the guy who invented the prefrontal lobotomy, a guy called Ygaz Moniz, collected his Nobel Prize for inventing the prefrontal lobotomy. I mean, warmongers get Nobel Prizes as they're sending troops to war, don't they? So this guy, medical doctor, got a Nobel Prize for destroying the most important part of our brains. And he collected his Nobel Prize in a wheelchair because one of his former patients shot him. Wasn't so happy with his cure. Okay. But anyway, Ygaz Moniz. Okay. So what he destroyed was the polar frontal cortex, and it's really, really important. And I'll tell you why. It's special because if these are the frontal hierarchies of speech, the hierarchies of spatial reasoning, the hierarchies of social reasoning, then the polar frontal cortex exists at the very apex of all those hierarchies. So its kind of place would suggest a kind of importance. And there's a difference between human beings and animals, and it's a huge question. Why are human beings smarter than other animals? And it's really a question that hasn't been satisfactorily answered. But I believe the polar frontal cortex is the difference that makes the ultimate difference. Now, a lot of you will be aware of the idea that chimpanzees are 1 or 2% genetically dissimilar to us. That's all it is, probably even less. And 2/3 of that genetic difference is to do with smell. So basically, chimpanzees, for some reason, we have an edge over monkeys and chimpanzees, and we're not quite sure what that is. But we know that the polar frontal cortex is vastly bigger in human beings than it is in other animals. Now, people thought the entire prefrontal cortex was bigger in human beings than animals, but they're not even sure of that now. But what is not in doubt is this. Okay, this is drawn to scale, so that's a monkey brain. Part of its prefrontal cortex, and that's a human brain. Can you see the orange area? That's basically area 10, Brodmann area 10 polar frontal cortex. Can you see the proportion of area 10 in the human brain is vastly bigger than in the monkey brain? And a chimpanzee is slightly bigger than a monkey. But can you see there's a huge kind of difference in a human brain? I'm going to show why this polar frontal cortex is giving us this incredible advantage over animals, and it's part of the fractal brain theory and the recursive thinking. And okay, we're going to go into a sub-talk within a talk. So we're going to examine the question of human and animal difference now. So we're going to kind of like a sub-talk within the main body of the talk. A very interesting question in its own right. Why are human beings more intelligent than animals? And also the interesting question of what is the difference between other human beings, genius and normal people? And also the difference between the same person but in a different part of their lives. So this is kind of a sub-talk within a talk. Now, okay, so human difference, animal difference. Now, for years, I mean, people thought absolute brain size and brain-to-body ratio was important, and it is. It's a factor. So, you know, these are all different brains drawn to scale. Now, it is important, and controversial research has shown there is some correlation in human beings between, you know, brain mass and IQ or other tests of intelligence. Now, controversial stuff, I know. But it's not the only factor, because that's an elephant brain. It's actually bigger than a human brain, so it's not the only thing. Now, some people in the past have thought of this idea of encephalization quotient, brain-to-body ratio. And it might be a factor, but again, it's not the only factor, because a pygmy shrew has the biggest brain-body ratio in the entire animal kingdom, so it's not the only thing. But it is a factor, so brain size is one part of the equation. Now, how many of you had one of those as a pet as a child? It's called an axolotl, and it's basically, the second factor is called neoteny. Scientists think we are clever because we are neotenic. So what does neotenic mean? Well, the axolotl is the kind of classic textbook example of neoteny. But what it is, it's basically a Mexican salamander that stays as a tadpole all its life. And they make great pets, especially if you're a child, because they grow big, like 30 centimeters. But you know, amazing fun, because you can, as a small child, you can go to the garden, dig up any creepy crawly, and they'll eat it. Amazing fun. I mean, so for a little boy, an axolotl and a box of matches, you don't need save a fortune on toys. I can't wait until my daughter grows old enough so Daddy can buy her an axolotl, so Daddy can play with it. Okay. Well, anyway, axolotl is basically a tadpole, but it stays a tadpole all its life. Okay, so it's basically a tadpole tiger salamander. Now the idea is basically we are neotenized apes, so that's a chimpanzee, and the idea is that this is the bone structure as an infant chimpanzee. Now, the basic idea is that we are neotenized chimpanzees, so that's a chimpanzee structure going across, and that's a human skull bone structure going across. Now the idea is that basically, can you see, that's a baby chimpanzee, that's an infant chimpanzee, that's an adult chimpanzee. We stay, bone structure-wise, as infant chimpanzees. Now the idea is basically, you can't teach an old dog new tricks, you can't teach an old chimpanzee new tricks. I mean, what you see in Tarzan, Cheetah is a young chimpanzee, he's playful and he's, you know, he learns things, but older chimpanzees are quite aggressive, territorial, and not particularly interested in playing with Tarzan. Okay. So the idea is we are neotenic apes, but we retain that playfulness, that kind of what scientists call plasticity. We've retained the ability to learn all our lives. So you can teach a human being new tricks. So the idea that we are neotenized apes is giving us an advantage over other apes, because we retain the ability to learn, basically, and be playful, and play as part of learning. Now the third factor is we're back to our striatum and cerebellum again. Okay. Basically, cerebellum and striatum is the skill and procedural learning. And one of the ideas the difference between genius and a normal person is that the genius has drilled himself or herself endlessly. And the idea, Malcolm Gladwell, the psychologist, talks about a 10,000 hour rule. The genius has basically focused on something for 10,000 hours. Endlessly drilled himself or herself. Michelangelo just worked obsessively, 14 hours a day, year in, year out. The Beatles, when they were playing in Hamburg, basically did more gigs in the space of a few months than most bands do in their entire careers, basically. So the idea that the genius is motivated either by circumstance or through just sheer will. Van Gogh, when he first started painting in his early 20s, wasn't that good, but in his mid-20s, he drilled himself in colour theory, literally read up on the latest colour theories, and drilled himself on how to mix colour. And so Van Gogh became this amazing kind of artistic genius through really sheer hard work. Now, the idea is basically you are training your cerebellum and striatum to basically be able to learn all these skills and procedures, essentially. So now, between animals and human beings, the cerebellum in a human being has far more scope and also the striatum than in other animals. So the idea is basically, if this is so important for intelligence, as we discussed earlier, so that's the prefrontal cortex. Now the idea is basically in a human, that's a human brain, a relay station to the cerebellum, that's a monkey brain. You can see the proportion of the green area, prefrontal cortex, in the human area. There's far more cerebellum to do with the prefrontal cortex than there is in a monkey. Now the idea is that cerebellum is also do things like a concert pianist rattling out, many notes per second, or kind of Yngwie Malmsteen or Van Halen, just bashing out like many notes faster than the brain can process. And that's because it's using the cerebellum. The idea is basically you're using a cerebellum, but in your prefrontal cortex. So you're drilling your thoughts to be like, the kind of concert pianist's hands on a keyboard. That's something we can do that chimpanzees can't do. That's the idea. And the same with the striatum. The idea that in the striatum we have more facility than in a monkey brain. So there's a very important ability to kind of automatize and make automatic behaviors. We have far more facility in human beings than in monkeys, and that's another reason why we're more intelligent than other animals. And the next one is spindle cells. This was quite hot a few years ago. Basically, as you go up the evolutionary ladder, the cleverer the animal is, the more spindle cells they have, basically. Dolphins, chimpanzees, and also whales have lots of spindle cells. Now, bonobos, chimpanzees called bonobos, have the most spindle cells after human beings. And they are a form of chimpanzee. Now, thousands of years ago, there's one kind of set of chimpanzees, and they live in Africa. But through some kind of change in geography, a new river formed that cut through the population of chimpanzees. So north of the river is your normal chimpanzees, but south of the river, bonobos evolved. Now bonobos spend a lot of their time standing on their hind legs. They stand on two legs. They have a very complex social structure. And they have all these spindle cells. And they also have this phenomenon that anthropologists have noted called G-rubbing. And it's like human beings shake hands and kiss each other on the cheeks to greet each other. Well, bonobos, they turn around and they rub each other's genitals. So there's another example of the speaker putting gratuitous sex into his talk and trying to perk up his audience. Okay, but anyway, so spindle cells are really, really powerful, really important. And the reason why is when we examine where they're located, because they're located in the what's called the anterior cingulate cortex. And the anterior cingulate cortex has been called by Francis Crick the seat of free will. It's also the part of the frontal lobes that forms a circuit with the nucleus accumbens, which is the part of the striatum that's part of the pathway of addiction. And it kind of makes sense, doesn't it? Seat of free will, pathway of addiction. What the spindle cells are doing, really, is relaying commands from the top, the command center, down to bottom. So spindle cells don't really process much information. They really relay information down. So this is a really important part of intelligence, the idea that from top down, you send those commands downwards. Okay. Now, there are other factors. I mean, the idea of a dopaminergic brain, that dopamine is the kind of chemical of addiction. Therefore, some people have overdriven dopamine pathways, make them more prone to schizophrenia and make them schizotypal, but they're high achievers. The idea of Einstein had thicker parietal connections and more glial cells. These are support structures. So the idea that he had better reasoning ability because he had thicker, it could be because he spent more time using his brain in that way. And there's other reasons as well. But the main reason, which I'll show now, why what gives us this amazing edge is we come back to the polar frontal cortex now. So we're going to looping back into the main body of the talk now. So basically, factor 5 is really the main one. These are all factors. They all work together really to give human intelligence. So it's not one or the other. They all work together. But the real critical factor is this polar frontal cortex. So we're going to show why now. Now the polar frontal cortex is special because it's at its apex, but also whereas all these parts of the prefrontal cortex connect with the sensory areas, the polar frontal cortex doesn't. It exists on its own kind of little kind of like a kind of unique privileged place. So what is it doing? What it's doing is basically it's doing recursive and multitasking thinking. So this is a brain scan. It's actually one brain. It's a meta-study. It's a composite diagram of hundreds of brain scans. So basically, the area green, polar frontal cortex, that's lighting up, it lights up when there's multiple tasks going on. So this is from scanning experiments showing that the polar temporal cortex is doing multitasking. But also, multitasking and recursive thinking are really closely related. And really, I'll explain what recursive thinking and multitasking means. Now, okay, that's the next diagram. Now, the fact that I kind of did a sub-talk within the main body of the talk and I jumped out, that's an example of multitasking and recursive thinking, because I did a recursion into a kind of sub-loop, then I looped out of it. Now, I'll give you another example. Okay, you're kind of, you're sitting at home, you're watching a DVD. Not that I watch DVDs, of course. I mean, I'm too busy reading science books. Anyway, you're kind of like you stop watching the DVD and you're hungry. So basically, you go into a subtask of going to the shop. You realise I've got no money in my pocket, so I have to go to the bank machine. And I basically go to the bank machine. I go to a subtask of punching the numbers in. I get the money out. Then I jump out of that subtask. Then I go to the shop and I get the food. And I eat the food and I go back to watching the DVD. Okay. So you see, it's basically like I need to store things on a kind of a storage area. Now we take this ability for granted when we realise, sometimes when we lose it. Now, when I was a bit younger, I used to enjoy myself so much on the weekends that I'd completely forget what I did. I knew I had a good time. I met loads of amazing people. I find women's telephone numbers with their names on it, and I think, who's that? And kind of midweek rolls along, and you kind of like wander into the kitchen purposefully. By the time you get there, you forgot what you went there for. Did you ever have that? No. Oh, excellent. Okay, I'm not alone. It's disconcerting. Now brains bounce back and brains heal, thankfully. But I mean, so this is what the polar frontal cortex will do. Going into a subtask, we need to remember where we came from. So it's actually quite important. An analogy with computers is important because in a computer, when we do multitasking and recursion in the computer, what we do is basically we interrupt the task we are doing, then we put the task we are doing onto what's called a stack. It's got like a memory center. And then when we finish that task, then we take back from the stack and we continue what we were doing. That's multitasking, basically. And also when we do recursion, the same thing. We recurse into a sub-level of the hierarchy. We have to put where we are onto the stack. When we come back, we take off the stack and we carry on, essentially. Now, in the brain, where this polar frontal cortex links up into is what's called the pro-isocortex and also the superior temporal gyrus. Now, if there's an apex of symbolizing and kind of compositing and kind of representing things, then really this kind of superior temporal gyrus and polar temporal cortex is really the apex of that symbolization process. The polar temporal cortex has been called a hub of meaning. And this is where the polar frontal cortex links up to. And then the polar temporal cortex is privileged because it has a direct link to the entorhinal cortex, which is the main relay station, to the hippocampus, the memory center. You see, just like in a computer, when we do multitasking ourselves and do recursive thinking in human beings, we have to put what we're thinking about onto this stack, onto this hippocampus via the polar temporal cortex. And in the same way computers need to store the previous state, we also have to do the same thing. So it's automatic until we lose the ability to do it, and we realize, it's something we take for granted. It's completely automatic. Now, this is a really important ability because this ability to represent things at the top of the frontal hierarchy, to represent it and then put it on a stack, means that once we can represent our minds, represent our language, represent our spatial reasoning, our social reasoning, once we represent our minds and put it on a stack, then we can analyze that representation. The fact that we can symbolize and represent our minds means that then we can study our minds. What it means is that we can do things interestingly. We can do recursive thinking. We can do recursive thinking with language. With our entire brains, we can formulate a sentence. But then we can put it on a stack and then go into a subtask of thinking of another sentence. And then we can put that entire sentence into our other sentence. So we can nest sentences recursively. That's really important, recursive language. But also spatial reasoning, egocentric, allocentric objects that I see my allocentric reason are basically form representation of this room different aspects of this room, different objects in this room, then I can put that on the stack. But then I can go out, I can form a representation of the corridor and the rest of the building. But then I can take the representation of the room, I can stick it on the representation recursively of the representation of the building. Then I can form a representation of the entire building, and I can put it on a representation of Bristol. I can put the entire representation of Bristol on the representation of all the motorways in England. You can see what's going on. I'm basically using this ability to store my entire brain state. But once I can store my entire brain state and symbolize it, I can then manipulate it and analyze it and stick it onto other brain states. And also social reasoning, the idea that we can represent ourselves and also represent ourselves in relation to other people means we can analyze ourselves. Once we can actually represent ourselves, then we can actually analyze that representation. And also, once we represent social situations, we can then analyze that social situation. John Ullman, the Caltech neuroscientist, he wrote a paper saying that the polar frontal cortex was to do with social reasoning. It is to do with social reasoning, but the real power is that social reasoning is powerful when it becomes recursive. It's more that the polar frontal cortex deals with recursive processing generally. Now things get really interesting when we represent our thinking. We actually represent how we think. But then when we can do that, then we can actually think about ourselves thinking. And we can also think about ourselves thinking about ourselves thinking about ourselves thinking, and then why the hell am I thinking all these things? Sometimes we get in these kind of dark loops of rumination, and and also positive loops of positive thought. Sometimes we think we're wonderful. Let me count the ways, and sometimes we think we're damn awful. And then kind of this endless recursive loops of thinking. And this is really I believe the essence of what makes us human. It's what Douglas Hofstadter, the computer scientist, said, that artificial intelligence doesn't have this ability to jump out the system, to represent itself and then jump out of itself, to analyze itself. And I believe this is what humans can do. We can do it socially, cognitively, linguistically, and spatially. And I think it's really, really powerful. What we're seeing in this first section is that the idea that that these features of the brain really emerge as basically things like spatial reasoning, language, prospective, retrospective memory, and also recursive polar frontal reasoning really exists as kind of parts of a fractal hierarchy. So in the context of a theory which is completely recursive and fractal, the polar frontal cortex really makes perfect sense because cell divisioning, a cell dividing to 2, dividing to 4, dividing to 8, that's a form of recursion. And when I link things up across, like I did with the combinatorial codes and loop things in time, that's also recursion. But that's recursion going into my brain, and it's limited. What this polar frontal cortex ability allows me to do is basically take this entire recursive process, but I use my entire brain to do recursion with. And that's really, really powerful. So in the context of a fractal recursive theory, this polar frontal cortex really sits on a kind of apex of that theory. And also, there's another feature of what I talked about earlier, language and also the sub-symbolic and the symbolic are really parts of the same fractal hierarchy. Also, what we've shown in this first half of the talk is that these problems of representing space and time, but also the problem of symbolizing and representing, they're fractal, and also the problem of recursive thinking, that the polar frontal cortex needs to symbolize and represent the work, that really these problems are really tightly interconnected, aren't they? Basically, the fact that space and time use the same language, then you use that representation of space and time to form composites in combinatorial spaces and language. So these way of looking at things, one is grounded in neuroscience, but these three aspects are so tightly interwoven that you don't really understand one properly without the other. And I believe this is the main stumbling block of artificial intelligence and basically of science. Why has the problem of working out how the brain works been so profoundly difficult? The problem of creating artificial intelligence has been such an incredibly hard thing to do. And the reason is because all the aspects of the brain are so tightly interconnected, you can't reduce the problem. So the way that academia works, the way that corporate labs work, they basically reduce, they compartmentalize, and they specialize. And the reason why they find it so hard is because it doesn't decompose into separate reduced problems. You have to actually tackle it all, or basically you're going to be really stymied. I mean, something that Peter Norvig, who's the director of research at Google, also an academic computer scientist, he said something interesting recently. He said all the problems in artificial intelligence are really, really hard. The separate problems are really difficult. But then he went on to imply that to take them all together is going to be much, much harder. What I say is the individual problems on their own are impossible. It's only when you do them all together that it's going to be hard, it's not easy, that you actually get a solution. So this is the reason I believe why artificial intelligence has been so hard. Now, John McCarthy, who's one of the grandees of artificial intelligence, he actually coined the expression artificial intelligence. He was there right at the beginning. Now, he says in an estimate, in an interview, when is artificial intelligence going to come? He says, the upper bound, 500 years. That sounds really like really pessimistic. Watching some of the recent talks at the 2012 Singularity Summit, you realise that his guess is actually being optimistic and generous the way they're going about it, really, because they're reductionist and they want their truths compartmentalised, but it doesn't work that way. So what I propose is this kind of completely integral way of looking at the brain that looks at all the problems in artificial intelligence together, but also integrates artificial intelligence with neuroscience, with psychology. And I believe this is the real key to creating artificial intelligence in a fairly shortish space of time. But anyway, another guy, David Deutsch, said to create artificial intelligence, some interesting and massive idea has to emerge. I believe that interesting idea is one of the main ideas in science, symmetry, that's how science works, but also self-similarity, fractals. But also, I'll show in the second half of the talk that this idea is also cosmic, that a real understanding of the brain really extrapolates into society and into the universe, and vice versa. The entire universe and the processes and structures of society interpolate into the brain. I'll show this in the second half of the talk, so don't go away. We're going to take a short break, and we'll be back in about 15-20 minutes. Welcome back. In the second part of the talk, we will continue in our investigations of brain, consciousness and cosmos, and now in the second part what we're trying to explain is what is the process of the brain and what is the process of life and how can we map that to the universe. So this is a very ambitious second part of the talk. It's hugely ambitious. It makes the first part seem a bit basic and mundane. Well, basically, the idea is that you have a fractal structure, but you also have recursive process. Now we have this fractal brain. The idea is that you have one language to describe the entire brain. You have one structure, but then you also have one language. So we are really aiming for grand unification here. So one language is our binary combinatorial code language, which we've described early on, especially in the first talk. And the one structure is this Russian doll hierarchical structure. Now this somehow, we've got to figure out this one unifying process for the entire brain. Now there's clues already because if the brain's fractal, then surely the process of the entire brain should reflect the microcosmic processes. And I'll just list what these microcosmic processes of the brain are. As I said earlier, one is competition that's going out throughout the entire brain. Representations, neurotransmitters, neurons, they're competing. And also linking up, neurons, representations, brain patches link up. Now, another one is what described earlier of the symbol. You can reconstruct from the symbol and you can also recognize to the symbol. So in a sense, that reconstructing and recognizing is sensing and doing, isn't it? So you're sensing something and you're recognizing something and you're doing something. So this is what we do, but this is also fractal throughout the entire brain because on a whole human level we do things and we sense things. But then in a sense, in our brains, you see in this earlier slide, in a sense, these projections going into the neuron, into the column, into the macrocosm, into the patches, in a sense that's it sensing on a microcosmic scale. And when it projects out, that's a form of doing, isn't it? So competing, joining up, sensing, doing is happening throughout the brain at all levels. And also symbolizing, again, recursive, fractal, throughout the entire brain. Now, if we have a fractal structure, i.e. the entire brain, Russian doll nested fractal structure, then because these components exist within that fractal structure, the basic idea is that all these fractal processes are recursive. So when I do something, then basically from my emotion centers, I issue a command, but recursively, lower down the chain of the command, they recursively do things when you get right until the motor cortex, when you actually move your arms and legs about. And vice versa, in the sensory cortices, when you sense things, you have basic autonomic sensory neurons, and they recursively then feed their signals to the next level of the hierarchy, to the next level of the hierarchy, etc. And also, this competing process, basically, when you make a decision, you were able to make that decision because neurotransmitters competed at a synapse. Synapses competed, neurons competed. And like a tennis match, these competitions percolate up so you can make a decision in life. You see what's going on? It's basically all these competitions, actually like a tennis match, funnel up into our overall brain states, and vice versa. When I can send from the emotion centers to actual expansion into autonomic movements. Now, this second part of the talk is ambitious, but it's really tricky thing to explain because, as I explained earlier, how the brain works is really tightly interconnected. So there's about 4 ideas, and they work really tightly together with one another. And when you consider these in isolation, then you have very simple artificial intelligence. It's only when we bring these ideas compactly together that we really understand how the brain works. Okay. Now, one of these ideas is the idea of mapping. One of the things we learn in maths is this idea of mapping. It's one of the most fundamental ideas in mathematics. The idea you take a number and it maps to another number. So any mathematical function is a mapping, basically mapping one number to another number. Now, in our brain theory, because we do everything in combinatorial codes and combinatorial binary space, when we do mappings in our brain theory, what we're doing is we're mapping a combinatorial code in one part of the brain, then we're mapping that to another combinatorial code in another part of the brain. So I can do this. Also when I take a cell and I divide it into two, that's also a form of mapping. Basically, taking a cell, I'm saying I'm mapping into myself, branching into myself. And because a cell doesn't exist there, I'm actually creating a cell. So mapping also describes neurogenesis. And also, I can map a pattern in one kind of cell or patch of the brain, and I can binary tree map it to another part. So I can sense a pattern here, I can map it over there, or map another pattern there, and vice versa, and also map a pattern there into another pattern. So I'm basically taking shapes or patterns, then I'm using that to map to another kind of a pattern elsewhere. So in the same way with language, I can recognize patterns and I can reconstruct patterns. I'm doing something slightly different. I'm recognizing a pattern, then I'm mapping that pattern to another pattern elsewhere. And I can do it in space. I can also do it in time. So if I have a pattern, then I can map that to a pattern in the next step. I can do it fractally with tiny parts of my brain. And with the striatum and cerebellum, I can do it with entire patches and with my entire brain. So this idea of mapping patches of combinatorial space to other patches, what I'm doing is basically I'm exploring combinatorial space. So in a sense, earlier on when I said, you can create these combinations using combinatorial codes laterally and also combinatorial codes in time, and there's an immense number of combinatorial codes you can create and a huge almost infinity of combinations you can create. Through mapping, I can create, like neurogenesis, create the substrate of the brain by mapping into myself. But then through mapping laterally, I can create patterns across other parts of the brain. And then by mapping in time, then I can create combinatorial representations in time. Now, can you see potentially I can map an infinity of potential sensing patterns with doing patterns. So potentially I can map and explore an infinity of combinatorial space. And also this idea of exploring combinatorial space is when we have evolution, when we have a stretch of DNA, okay, it's four bases, but we can binary code it. When we flip a bit, or flip a kind of a stretch of DNA, that's also exploring combinatorial space. But that's also a mapping. You're basically taking a stretch of DNA, and you're saying a mutation. You're mapping that strand of DNA to a mutated strand of DNA. And you can do it randomly. You can keep kind of randomly kind of changing the bits. But can you see that's also exploring combinatorial space? And because it's fractal, if I flip a bit, that's exploring combinatorial space. If I have a patch of cortex and I map that to another patch of cortex, a pattern in T+1, that's also exploring combinatorial space. If I move into a room and move my arms and legs about, I could point over there, I could point over there. These are separate explorations in the combinatorial space. And because this language of combinatorial space it describes the entire brain and all our representations, this idea of mapping really is a way of actually expressing all our behaviour. And all our behaviour breaks down into these sensing and doing couplings. We see this throughout the brain. So neurons, dendrites flowing in, maps to a pattern flowing out. Okay, so this is absolutely ubiquitous. And stimulus response, I see something, then I see a traffic light, it's red, it maps to stop. Then it turns green, that maps to foot on the gas. So these are mappings. It's a very generic way of saying things. So exploring combinatorial space with mappings in time and space, but also flipping bits randomly, is really the same language. And we see this at work when we see baby babbling. Now the brain is a very noisy environment. It's not kind of still and deterministic. It's actually really, really noisy. And when babies babble, what they're doing is they're exploring combinatorial space. So basically eventually those babblings become words and become speech sounds that fit with the accent and language of the parents and the sounds they hear. So babies exploring combinatorial space, then eventually it fits a kind of like a pattern, the kind of target pattern. Now the question is, now I can explore, hierarchically represent this infinity of kind of possibilities. Now with combinatorial codes throughout my kind of millions of cell columns and billions of neurons, I can potentially kind of explore and babble and kind of mutate myself to an infinity of possibilities. But I can't represent an infinity of possibilities. Therefore, I have to select a certain number of possibilities. So we need to, if we can generate these patterns, the baby babbling, there must be a way of selecting certain babblings over other babblings and work on those. It's basically a process of competition, of ranking certain babblings to other babblings. So a process of competition where we can actually select certain combinations that are more advantageous than others. So what we're talking about is really meaning, purpose, and salience. So how do we give meaning to the brain? And how do we give meaning to artificial intelligence? So now we have to explore the emotion centers. Okay, we're going to revisit a thing we covered a lot in the last talk, but we're going into it in a special way this time. Okay, the emotion centers. We're going to give the brain meaning and purpose. Now, just to quickly recap, the emotion centers on 3 levels: hypothalamus, amygdala, and ventral medial prefrontal cortex. Now, it's just a quick skimming stone recap. The hypothalamus deals with the most basic rewards and aversions, and it's got the hierarchy. It gets more advanced and more complex and up the evolutionary scale. So, just one example, say, well, hunger. I mean, hypothalamus will detect glucose levels, and then if you satisfy a certain level of glucose, then you're not hungry anymore. So it's basically, it does hunger the most basic way. And then the amygdala and ventral, that does taste. So basically, you're interested in how certain foods taste. And also that deals with things like smell and more complex processing of food. Now, this axis of our emotion centers deals with all our concerns, all our aversions, and all our desires. And it's on an axis from simple to more complex. That's the hypothalamus. I'll just quickly skip through. That's the amygdala here. And that's the, that would be the prefrontal and ventral medial prefrontal cortex. Now, the emotion centers and meaning, I mean, in the last talk, it was really about reward. So emotion centers are rewarding, like, reinforcement of behavior. But there's really kind of a dual axis between all these kind of aspects of our emotions. And it's to do with dark and light. Now, if the first talk was like Star Wars, it was all positive and bright and reward and fix and addiction and nice, and this is like more like Empire Strikes Back. It's about the dark side. And it really, for all these emotions, there's always a dark side. So homeostasis, there's actually reward of getting food, but it's also the kind of aversion of being hungry. There's also the kind of like sweet spot of feeling just right and feeling not too cold. And then there's a kind of And then there's the kind of a negative surround of feeling too cold or too hot, and with thirst, etc. But also, this is a fractal concept because, I mean, also with they have conditioned place preference, where a mouse or a human being will prefer a certain place, find it rewarding. But it's also contextual fear conditioning. So light and dark, negative and positive. And, so it's really throughout, and in more complex things. I mean, there's kind of like the kind of pleasure of sex, but there's also the kind of negative of sexual craving. And one of the highest feelings of love, the pleasure of love, 1,000 pop songs written as odes to love. But then there's a kind of negative surround because the Carpenters say, awesome voice, awesome act. I'm showing my age, you see. I remember the Carpenters. Incredible songs. And most of the songs they wrote were about not being able to find love. And it came from the heart because Karen Carpenter really couldn't find love. And her brother who wrote the songs couldn't find love. And her brother's friend who co-wrote the songs couldn't find love. So she sang about we can't find love, and it really came from the heart. And another example, well, a slightly different example, was ABBA. In the latter part of their careers, most of the songs were, we were in love, now we're divorced, and it's really ghastly and it really sucks. So the boys write the songs, and they're really feeling it because they're living it, and then we sing the songs, and it really comes from the heart. Anyway, I mean, you get the picture. There's kind of like a positive, this thing called love, and around it there's kind of negative aspects. But this is really something universal in all our emotion centers, in all our emotions. It's kind of light and dark. So it's what I call the carrot and stick of motivation. To all motivations, there's a reward, but there's also a stick. The carrot and stick of what makes us tick. And in the last talk, I talked a lot about addiction. Yes, addiction is a fix and it's a reward, and you want to do it again, but it's also the stick of, you take an addictive drug, you get that fix, but also, almost without exception, addictive drugs suppress the anxiety center called the central nucleus of the amygdala. You smoke a cigarette, drink alcohol, tranquilizers, heroin, THC, cannabis. You get the rush, the fix, but it suppresses your anxiety centers. And when a drug wears off, you feel anxious. You feel like cigarettes. So there's a reward of the rush, but there's also the suppressing of the anxiety. And reinforcement, back to the striatum, when you get a reward, a fix, the dopamine levels rise. It's what's called frequency coding. I mean, the dopamine levels always flow, but when you find reward or something unexpected rewarding happens, it rises. And heroin and crack cocaine, they're basically is the same as cocaine and morphine, because heroin is basically triacetylmorphine. What goes into your brain is morphine. But it's frequency coding. The frequency, the amount that goes into your brain is a real rush, and you get more of an intense hit. So that's reinforcing, addictive. Now, conversely, when you feel frustrated or you're disappointed, you expected a reward but you didn't get it, the dopamine levels drop. Now, very recent research has shown basically the synapses to do with the prefrontal cortex and the striatum, also the pathway of addiction. When the dopamine levels drop, then the synapses weaken with the signal. When the dopamine levels rise, then the synapses strengthen. That kind of makes sense, doesn't it? If you're expecting a reward and you're disappointed or you feel kind of frustrated, then you want to weaken that signal. And when you get the fix, you want to strengthen it. So carrot and stick of motivation, carrot and stick of addiction. And these really correspond to the basic conditioning paradigms of psychology, escape, punishment, reward, emission, etc. Now, so, emotions, fear and desire, what drives your behavior and what you feel as pleasure and pain is light and dark, and there's a kind of duality throughout all your emotions, all your drives. Now, it's interesting because with the rest of your brain to do with sensory cortex and prefrontal cortex, this same pattern of light and dark, of activation and suppression, is also found throughout the rest of your brain. So this pattern of a cortical column suppressing its neighbours, the winner suppresses its neighbours. The idea of, in all these sensory pathways, there's an activation centre and then it suppresses its neighbours, a kind of lateral inhibition it's called. And also in a striatum, this idea of Mexican hat activation function. We have an active region of the striatum, all the surrounding regions are kind of deactivated. and also in the cerebellum. So throughout the cerebral cortex, cerebellum, and striatum. And also in hearing, this idea of auditory masking, that when you hear a sound, the dominant sound will suppress its neighbours in space, frequency slightly above, frequency slightly below, but also in time, slightly before and slightly after. And the striatum, hyperdirect, direct, indirect, in time, is a kind of suppression, then an activation, then a suppression. You see a kind of picture of a kind of like a kind of light center and a dark surround, or kind of a light and dark necessary for your senses and your motor activity to work. So when you do things, it's not just about activating something, it's also about suppressing something. We know at the highest level, your prefrontal cortex isn't just about activating behaviors down below, it's also about suppressing behaviors down below. And also paying attention isn't just about, receiving signals, it's also about suppressing competing signals, and also perception as well. Now, I'm going to make a huge conceptual leap, okay? Now, because it's a fractal brain theory, this is a huge conceptual leap. And what it is, it's this. Now, some of you might remember from the previous talk, okay, I'll recap, because it's really important points. It's a massive conceptual leap for our fractal brain theory. Now, that's all your kind of prefrontal cortex to do with thinking and to do with moving, right down to your kind of primary motor cortex to do with actually moving your muscles about, okay? And that's your emotion centers. Now, in the last talk, we put it on one hierarchy, and we justified it because the emotion centers have the same striatal kind of architecture as the rest of your prefrontal cortex. And also has its own, all the emotion centers have the same kind of dopamine architecture as the rest of your prefrontal cortex. And also there's a wiring pattern which makes this kind of concatenation of all these different parts in one hierarchy make total sense. So in a sense, what we've done is basically we're given, if these parts of the brain are to do with space and time, i.e. space and time topographic maps animated in time, then what we don't normally think of spatially and temporally is the emotion centers. But what we've done is basically we've spatial temporalized the emotion centers. I.e. we've given the emotions space and we've given the emotion centers time. Now this makes sense because emotions, we're not actually interested in static emotions, we're interested in changes of emotions. We're not interested in being hungry, we're interested in the being hungry, and suddenly something happened and we're not hungry. That's what we're interested in, something happening in time. And also it's sensible to talk about context of intent, context of frame of mind. And also when we look at things in a hierarchy, hypothalamus, amygdala, and ventral and medial prefrontal cortex, it makes sense to talk about context. It makes sense in the context of sexual pursuit and sexual reproduction, hypothalamus, orgasm. It makes sense to talk about the amygdala handling gender preference and pheromone processing in the context of sex. It doesn't work otherwise, does it? And in the context of hypothalamus, sex, and gender preference, then it makes sense to talk about square shoulders and kind of buttocks and breasts and stuff. I mean, in the context of sex, gender, and attributes. And I know Dumb and Dumber, that movie. Sorry, cut this out probably. Dumb and Dumber, that movie, Jim Carrey. I mean, I can watch it again and again. It's so funny. It's so really funny. I've said it about 100 times. I mean, that scene when they're walking down the street in Aspen, and then Jim Carrey was with his friend, the bloke, and then he sees his couple walking by, and then Jim Carrey's friend says, "Check out the butt on that one." And then Jim Carrey says, "I bet he works out." Now you see context of context, hypothalamus, sex, gender orientation, and then things like men looking at women's backside. So Jim Carrey's done something, out of context. You see, it's a context of intent. So, okay, cut a long story short. I've given the emotion. Okay, I've given the emotion centers. You see, space and time, context, time, temporal progression, but also spatial context. Okay. Now that was quite a bold conceptual leap in the last talk. Actually, put this in one hierarchy. But now you see, I can go the other way. You see, I've shown this light and dark to do with the emotion centers, and I've shown this kind of pervasive light and dark, activation, suppression, negative, positive, to do with space and time. What I say is basically what we reason as light and dark for the emotion centers, we can completely extrapolate for the rest of the brain and vice versa. It's just that we feel at the top of this fractal hierarchy of pleasure and pain, light and dark, we feel the apex. But then what we feel in terms of pleasure and pain has come from all the lights and darks and suppressions and activations and competitions lower down the hierarchy. So what I've basically done is I've basically fractalized pleasure and pain, light and dark. And later on, we'll make an even huger conceptual leap when we extrapolate the brain to the universe. Then it becomes a way of understanding this cosmic battle between good and evil later on in the talk, and showing it's really key to understanding it. Okay, so see what I've done. So basically, emotion centers given space and time, vice versa. What process of space and time has been given light and dark? But it's actually one and the same and one continuum. So hugely ambitious kind of stepping stone to something later on, which is even more ambitious. So okay, so we have now given the brain a sense of good and evil, light and dark, and some things we prefer, some things we find aversive, and some of these would be hunger, sex, warmth, etc. We can represent these in the brain. Now, light and dark has a meaning because it's not relative. Basically, we tend to avoid things which are pleasurable, and acquire things which give us pleasure and maintain them. But we also eliminate and avoid things which are aversive. So there's kind of a kind of active force going on. Can you see? So again, the kind of active kind of force to our kind of quite static view of the brain so far. We've given a kind of emotional force to the brain. Now, okay, so emotion centers. What we need to do now is basically we need to construct our realities from around these emotion centers. So we have a way of representing an infinity of possibilities with our combinatorial space, representations, and our kind of mappings that can represent an infinity of combinations. But we want to select a tiny subset of those representations to represent. And the way we do it now, because we've got meaning and purpose, another computer simulation just to illustrate the point. Okay, this is called a diffusion limited aggregate, and basically what it is, it's a central particle, and that central particle is sticky, and these points around it jiggle about with Brownian motion. They stick to the central point. Now what I'm saying is we have these sticky points of meaning, and they are to do with, I was hungry, glucose was low, then suddenly glucose is all right now. I was cold, and I stand over here, I'm less cold. Okay. So we have these kind of like central reward points. Orgasm, the kind of like, the reward, the kind of like fix, whatever, becomes your central point of meaning. So these become like sticky points you're born with and they're hardwired into your brain. But we also have points to do with aversion. Now, in brain space, basically, we start from these central sticky points, and what they are is representations in the hypothalamus. Then what we do is we have to now detect, we're trying to grow out our realities, all the things we know, understand, and do from these central points of meaning. So I'm saying that all meaning and purpose really derive from these central points of homeostasis, but also of fulfilling our requirements to reproduce. Okay, so I'm saying this is where meaning comes from and purpose, our emotion centers. Okay, now there's another trick we need to do. Because once we have these central points of meaning that are hardwired into our brains that are evolved, we need to find those patterns which predict that reward or predict that glucose, that fix. Now, okay, another idea I'm going to introduce, which is really, really important, and it's one of the most important ideas in all artificial intelligence. Now, this is, it's called Bayes' theorem, okay? And basically, we have these emotion centers that have these kind of reward points. We want to basically ascertain what predicts those rewards or what predicts that aversion, that pain. And what it is, this equation, it's really simple. In fact, you could have, by accident, as a school child doing your O-levels, GCSEs, you could have basically shuffled around basic formulas in, basic high school mathematics in probability theory, and you could derive the Bayes' theorem. Now it's really simple. What it means is that it means that basically you're basically trying to predict the probability of A given B. So you're trying to predict, the fix, the orgasm, the rush of glucose, the reward given B. But the trouble is you don't know what B is. You're a newborn baby. You're new to this world. You have no idea of the world. You have to basically predict what predicts that reward. So what we do is we what Bayes' theorem is the equivalent of. Now, Bayes' theorem was also called inverse probability. Now, it's really simple. I mean, don't just put you off, because what it means is that basically, can you see, we're trying to find A given B, but this part of the formula, we can work out A given B from B given A. Now, cut long story short, it's much easier to find B given A because I'm trying to predict what predicts what my kind of fix, but I've no idea of the world, and there's a million things, 1,000 things out there which potentially predict my reward. And I can't keep track of those thousands and thousands of things because I don't know what's going to do it. But it's far easier to work backwards, backward chain, and also do reverse probability. Once I have the fix, then I look around and I feel around, and then I have a smaller subset of things which happen around that reward. You see, it's far easier, there's a far smaller subset of things to keep track of, working in reverse from the fix backwards. And this is Bayes' theorem. Now, this is probably the most fundamental theorem in all artificial intelligence. I mean, really, I guess, yeah, in a sense fundamental, but I mean, it's a simple idea, but all artificial intelligence techniques in operation today, the successful ones, use it in one form or another. Watson, IBM's Watson, expert systems, spam filters, they use Bayesian analysis. So it's really, the company Autonomy, which is Britain's biggest technology company for many years, got sold to an American company recently, is based on Bayes' theorem. But what it's doing is simple, but the brain can do it. Basically, what I'm doing is I'm reverse predicting stuff from reward centers. What allows me to do is to go back to this program here. It allows me to start from these points of reward that are hardwired into my brain. Then it allows me to backward inference and backward chain all the things which lead to that reward. See what's going on? So I'm constructing in an infinity of possibilities that I know nothing about, that I can potentially represent. I'm representing a subset of those possibilities in reality that relate to rewards and aversions. Okay, now I'll introduce another metaphor to explain something really complex. Okay, this idea that my senses are like locks. And by using Bayes' theorem and backward chaining, I am basically picking out the locks which predicts rewards and aversions. Now back to the mapping process earlier on of projecting out. If you imagine that evolving process of exploring combinatorial space as making keys, then the problem becomes one of finding the locks in reality which predict rewards and aversions, but then finding the keys which match those locks in order to realize those rewards and avoid those aversions. So in this kind of language, basically a baby babbles. What a baby's doing is evolving, exploring combinatorial space, and it's fitting a lock of a certain speech pattern from the parents. But this generalizes because everything in the brain is represented as combinatorial space. And basically everything, all senses can be represented as locks. Now, explain this lock and key concept now. Now, just to explain this lock and key concept a bit more. Now, you understand normal locks and keys. They're basically a certain shape, a certain kind of shape fits a lock. If it's the right shape, it will turn. Or if a combination lock, you need to press the right numbers. If you press the right numbers, then it'll work. So you have a pattern matching with another pattern. Now, a very simple diagram. What we're doing here is, over time, we have two binary patterns. You see the bits. Now that's perfect correlation. It's almost as if two patterns side by side is correlation one, i.e. it fits perfectly. The key and the lock fit together, can you see that? And the patterns don't quite fit. There's no correlation here. And here you have a partial correlation because some of these patterns fit one another. So in the same way, a physical lock fits a key, to a perfect fit will turn the lock. Here, a perfect match is correlation one, and it's to do with two patterns in combinatorial space, binary patterning combinatorial space. And the same here, except we got a bitmap here. You see, that shape here is exactly the same as it. If that's the key and that's the lock, then that's a perfect fit. So it means correlation one. Now here, that's the lock, but this is the key, and it doesn't quite go in, so the correlation is less than one, so it's not quite perfect. You get a picture? Now the idea is, I can use my emotion centers and I can form these locks, but these locks actually correspond to all the things I can sense. But what I do is I chain all these things I can sense towards my aversions, or away from my aversions, or to my rewards. And the trick of intelligence becomes finding the keys which match the locks. Okay, now okay, this is another example of backward chaining. So from a reward sensor, I form a lock, but then I can form a key to fit the lock. And once I form that key to fit the lock, then I can form a lock around a key. You see, these are those mappings again, dendrites going in and out. And I can backward chain to form those structures earlier, those growing from the reward sensor. Now here's where my innovation later on comes into play now. Okay, so here we go. Now, that's a photomosaic. Okay. Now, imagine you have a lock and key for your emotion centers. And the emotion centers, because I've fractalized light and dark, and I've spatialized the emotion centers, and I've shown that the emotion centers and the parts of the brain to do with space and time are actually one and the same. They're actually one hierarchy. Because it's fractal, what I reason for a key and lock in terms of, say, a bit pattern, I can see a bar of light to a template, or a baby babbling a kind of speech sound matched to its parent's voice. Okay, what I reason with lower down my mind hierarchy, I can also reason for a lock which represents my entire emotional state, all my context of intent, light and dark, all my aversions, all my pleasures become a pattern of lock. And then I match my state of my life to that lock. But this lock is like the overall picture of my life. Now that's a photomosaic. It's Mona Lisa, but can you see it's actually made up of other portraits. Now if you take this idea of a photomosaic fractally, I can go off into infinity. There's a way of looking at the brain exactly in this way, of basically the top tier, the entire brain being your context of yourself, your entire brain basically. Then the first kind of level of the hierarchy becomes your hypothalamus and amygdala, and that basically defines contexts of intent. And we can color these contexts of intent aversive or pleasurable, light and dark. But that becomes a pattern, a lock, into which we fit the state of our life. So, okay, back to this happy face. If that is actually the photomosaic of your entire kind of context of intent, then that's the kind of happy state you want to be in. But if one of these squares that represents dark is filled in light, it means something aversive is present in your life. So you have a mismatch. And if you have one of those squares which is colored light is dark, it means something which you find pleasurable is missing. You see, then there's a mismatch. So say I was warm, I was homeostatically imbalanced, and somehow that balance has upset, then my key has been mismatched with my lock. So what I'm saying, I can represent all my homeostatic needs in this way, and I can represent my entire kind of state of mind as a lock and key. So what I'm talking about is a master lock and key of all your homeostatic states, which you have to satisfy, or else you're in homeostatic imbalance. Now, but we are more than our homeostatic states. Things get interesting when we basically realize that as human beings, we're more than just satisfying our hungers and desires. Even though if you're living in the third world, that's what you spend your entire life doing, trying to satisfy these basic things. What we also do as human beings, we project prospective memory, we project a vision of ourselves into the future. As human beings, we create ourselves, don't we? It's not just, once we satisfy our basic drives, we create ourselves, and often we have a dream and ambition. Often that dream and ambition is linked up with finding your kind of marriage partner, or just finding someone to be with. But often in London, a common aspiration is to make it in the arts, music or acting or whatever. People come from all over the world to come to London, and that's an aspiration, a kind of lock. People form their minds. So once we've satisfied all our basic needs, we prospectively project an ambition, a kind of like an aim, ultimate goal in our lives. But that's a prospective lock in our future. So once we have that kind of all our homeostatic needs satisfied, then our lives involve assembling the pieces of our lives to realize that dream. And sometimes, what we dream doesn't make us happy. Sometimes we realize our dream, and often the dream is quite mundane, just find a job and get married. But that's what we do as human beings. Now, we have this way of looking at the entire brain and process in terms of locks and keys, and basically becomes a matter of finding what those locks are in terms of most simple the drives and desires, but finding the lock for our ultimate aims, and then finding the keys which then fit the locks. Okay, but in life we are basically partial solutions. We are partial locks. We are partial keys. Some of our keys and locks are incorrect. Some we want things, but they don't turn out to be the right predictions of what's going to make us happy. And generally, life is impartial. We don't quite make it. What we will explore in a minute is what happens if you get a perfect score. What happens if you literally perfect all your homeostatic needs, realize all your basically you perfect that process of life. What I've got ways is basically showing your entire life, all your homeostatic drives, all your desires in a kind of language where I can define perfection, i.e. correlation 1. What does it mean to actually have a perfect score? Okay, this is where we'll go into the realms of mysticism, mythology and religion in a minute, because religion, mythology and mysticism says something about this perfect score, okay, which I'll use this fractal brain way of looking at things to explore in a minute. But first, we need to do something. We need to basically revisit our sacred cosmology. Okay, just quickly revisit our sacred cosmology before we show this mapping from the human life to the universe. Okay, it's huge subjects we're dealing with here. The idea is that basically the brain is fractal, and also the universe is fractal. That the brain extrapolates to the universe, and the process of the recursive process of our brain extrapolates to the recursive process of society, the recursive process of history, and the cosmic recursive process. That's the essential idea. Now, the idea of extrapolating from the brain into the universe sounds really outlandish at first, until you realize that this is what scientists are doing already. Because scientists already think in terms of a fractal universe already, and also think in terms of the universe being informational, computational, and discrete, i.e. griddy and quantized. And also the universe as information and a computer. And also the idea that evolutionary theory is a master theory. So scientists are already saying that evolution is going on in the brain, and this I think they're correct. But they're also saying that evolution is a master theory happening in society and the entire universe. And this idea that they're looking for this kind of grand unifying theory of complexity. Complex things, all things in the universe, there's some unifying idea behind everything in the universe. So in a sense, scientists are already looking in this way. But the idea is basically, we don't understand the universe now because it's so big and there's so many different versions. But the brain is finite and complete, but we can understand the brain. The idea is that you don't interpolate from the universe society into the brain, you extrapolate from the brain into the universe. And that allows us to understand the universe. So that's the basic idea. And scientists at first, when they hear this, they say that's outlandish, that's mad. But when they realise it's what we're thinking all along, it's just make it clear to them. Now, this idea, this brain theory, unifies, and this extrapolation of the brain theory to the universe unifies three major ideas, and they are: one, how the brain works. Secondly, this thing called ontogenesis, how bodies come into being. But also the process called phylogenesis, how evolution works. So in a sense, we've shown this already. I mean, in the last slide, we have a brain theory which is evolutionary, that is discrete quantized and is informational. And what we need to show now is basically how is the universe fractal, and how does the brain correspond to that fractal? Now, okay, the human being starts from a fertilized egg, and that fertilized egg goes through a process of cell divisioning. So the fertilized egg becomes 2, becomes 4, becomes 8, 16. Now cells compete to play their roles, and the winning cells play their roles, and the rest they go by the wayside. And cells link up: bones, sinews, skin, and nerves. Somehow all these cells become the organs in your body, and these organs link up to become you, yourself. But this process of competition and cells differentiating and cells linking up is really evolution in your body happening. So in the same way, evolution of life on Earth starts from a common ancestor, dividing out trees and animals in divergent lines. Then the one world, all humanity, starting from a kind of singularity, a kind of point somewhere in Africa, spreading out, competing, fighting, joining up nation states, clans, tribes, trading blocks to this coming global village. And that's one of the issues of the age. Is this global village, one world order going to be a kind of horrible tyranny, or something better and more just and equal? But you see, the same process of diverging and competing and converging into one, that if within the process of ontogenesis, my body coming into being, is the process of evolution happening in the microcosm, you see, then the process of ontogenesis, bodies coming into this world and animals coming into this world, is happening in the kind of process which is phylogenesis, evolution. It's also happening in the process of the ontogenesis of this coming one world order, that humanity becomes as one. And there's this idea that it has to be just and fair, or else it's not going to hold together. It's going to be, and also this idea that somehow humankind is alienated from nature. This idea that somehow we are separate from nature. That in the same way that humans and plants and animals come from the same source, that eventually we will integrate as one. That humankind's separation from nature becomes healed. And that's almost like destiny of this process, And then we take this process to the universe, that the universe starts from a singularity. And then through a process of, planetary consciousnesses competing and joining up into galactic consciousness, into intergalactic, into pangalactic, to the cosmic Christ and this kind of universal Vishnu and celestial Buddha. But can you see, phylogenesis, evolution, nested within ontogenesis, ontogenesis within evolution on life, nested within ontogenesis, nested within the ontogenesis of the cosmic Christ. So it's really one process, interleaving, Russian doll and kind of interlinked, but it's really also the process of the brain. And I'll show you exactly why. Now, we are more than our brains, so our physical bodies come into being and our brains form, but a process unfolds in our minds. It's basically this process unfolds. If we came from a fertilized egg, then this fertilized egg becomes our bodies and brains, but then our minds go through a process. It goes through a story. And the story often and generally, the template is that leads to men and women getting into a position where they can fertilize eggs again. And that's the kind of human life cycle. Okay, now it is deep, and I'll show you, it is cosmic in a minute. Okay, so fractal universe, and somehow the mind, our life stories and the process of our lives is part of this fractal process. Now, okay, there's one thing missing. Some smart people are saying that, differentiation of cells in our bodies is like mutation, and it's like, evolution of species, the differentiation of cells, differentiation of species. But they're saying, surely that's controlled, it's controlled by the DNA. But isn't evolution random? Isn't the universe, the progression random? Isn't, evolutionary theory doesn't talk about random mutation? Well, okay, randomness, this is quite a heavy metaphysical point, but it's important. Randomness can only be a statement of what we don't know. It can never be an assertion of what actually is. And this has been proven by a guy called Gregory Chilton. He basically works a lot of Gödel's theorem, and he works with something called algorithmic compressibility. It means you have a string of numbers, or kind of any kind of pattern. Algorithmic compressibility is when you can actually find a kind of algorithm or some kind of formula which can compress all that complexity into something very simple. So the numbers of pi go on to infinity. It looks really random. Once you understand it's pi, then you can reduce it to one symbol. Now what he proved was basically, given any kind of string, you can never prove that there will never be a shorter compression of that string. So when you say it's random, it's only saying that we can't determine yet, a kind of more succinct way of describing it. You can never say it'll always be random. It's like you can never say the map is the same as the terrain, as anyone with the new iPhone knows. I mean, really, the map and the terrain is different. This is a mistake that scientists make again and again. The map is scientific theories, the terrain is reality. It doesn't necessarily correspond. So when people say random mutation, is really just a kind of shorthand for saying we don't know, we haven't discerned a kind of higher purpose and a higher pattern. Okay. Now, if not random, then what? Then how do we bring back purposefulness to the universe? If it's not random, why should the cosmic Christ, the celestial Buddha, emerge? What is the corresponding kind of determining of all these seemingly random mutations that are not random? What is making the universe purposeful? In the same way DNA converges to this body through a kind of controlled process. What is that corresponding process? Now this is a set of ideas which is going to really make a comeback, and it's very new. I couldn't have given this section of the talk 10 years ago because these new ideas are very new. And what it is, it's this idea that, and this is something we need to add to our fractal cosmology, to make it sacred. It's also a return of very ancient mystical ideas. Now, there's a recurring idea in science and also in mysticism and religion. It doesn't go away. It doesn't go away. It's the idea of a cyclical universe, that the universe is cyclical somehow. Now, even though it seems contrary to some of the latest findings to do with the acceleration of the universe, top scientists stick with this idea of a cyclical universe, and there's one reason for it. That reason is symmetry. It's simply because everything in the universe is cyclical. Atoms, changing of the seasons, rotation of the planets, rotation of galaxies. Everything's a cycle and sound and cyclical. And it'd be absolutely obscene if the universe wasn't cyclical. So this is an idea of beauty and symmetry is making these scientists say, no, despite the latest kind of superficial findings, the universe is cyclical. Now there's a new idea that's only come out in the past 10 years, and it's the idea that before the Big Bang, there is something. The Big Bang is not the beginning. So for many years, people thought Big Bang singularity is the beginning. There's this idea coming from science, coming from the two main camps in terms of the grand unified theory, string theory or M theory, and also the other camp called loop quantum gravity. And what they're saying is basically the Big Bang is not the beginning, it's basically the big bounce, it's the point of reflection, that something exists before the Big Bang. Now, this is not a kind of out there idea, because there's been two main articles in Scientific American magazine, which is one of the most prestigious science magazines in the world. In 2004, 2008, there's two long articles about this by prominent scientists. So this idea is actually coming to the fore, and it needs to be encouraged because it gives us an amazing return of an ancient idea. I'll tell you why. Because this is a diagram to show different ideas about the universe. Big Bang expands, and then Big Crunch, and then this is the idea of a Big Bang, a Big Bounce. Now, okay, a finding from one camp, the M theory, string theory camp, is basically they found basically in the pre-Big Bang epoch. Okay, they're saying basically, according to their equations and what they're finding, they're saying that universe is actually a mirror image of this universe. So you see, universe, that's kind of mirrored. So the word universe in that one, deflation, expansion, is a mirror image. Now, there's an important result. Okay, there's an important result in science, and it's an established result. It's called CPT symmetry, and it's basically a result. Nobel Prizes duly handed out and earned this time. So in 1957. CPT symmetry is this idea that charge, polarity, and time, they're interlinked. So with particles with the entire universe, charge, polarity, and time are interlinked. If you flip one, you have to flip the other two. You flip the other two, you have to flip the other one. You get what's going on. Now, because CPT symmetry, and because they're saying this universe is a mirror reflection, what it means is that pre-Big Bang epoch is the time reversal epoch. Now, what it means is that, now this is a question in science, because all the equations of science in relativity, quantum mechanics, and also Isaac Newton's laws of motion, they're all time reversible. They work equally well forwards in time or backwards in time. This is one of the puzzles of science. Why does time only flow forwards? And the simple answer is it doesn't only flow forwards. It flows forwards in this epoch. From the pre-Big Bang epoch, it flows backwards. But if the Big Bang is the point of reflection and not the beginning, then what we think of as forwards is actually backwards. I know this is a real head twister, so I made a diagram to... what it means, okay, this diagram, you see, if that's the Big Bang and kind of diverging out, so it's just a simple schematic to show the diverging out from a Big Bang, a singularity. And this kind of corresponding section here is basically, it's also the universe, but it shows a kind of converging process. You can see these circles, if these are like Russian dolls, as we go forwards in time, take a slice through time, then we have three big Russian dolls that haven't come together yet. By the end of time, these three big Russian dolls have integrated into the bigger Russian doll. You can see what's going on. So we start from total primordial chaos, and eventually we get to the cosmic Christ. Now, the idea is that basically, if the Big Bang is the point of reflection, then the beginning is the counterclock phase. So the idea is basically, we start from the cosmic Christ, the celestial Buddha, the universal Vishnu. Instead of starting from nothing, we start from perfection, wholeness, and oneness. And then, as the ancient scriptures say, going backwards in time now, through a process of dissolution and the breaking down of God, separatedness, Kabbalah, somehow the breaking of the vessel, somehow, God creates a universe through a process of progressive emanation recurring idea in Hinduism that the body of God becomes the universe, and for an eternal cycle, the universe becomes the body of God again. In mythology, the idea that the body of God gets cut up in little pieces, that becomes a universe. And so if that's the beginning, then that's forwards in time, the creation of the universe, forwards in time, beginning of the universe, until we get to the big bounce. Then as we go forwards in time, we're actually going back to the beginning. And because it's a complete mirror image of the pre-Big Bang epoch, inevitably the universe will converge back to the cosmic Christ, because that was the beginning in the first place. And it's a complete mirroring. The big bounce will be set up to actually come back to the cosmic Christ. Now, there's huge political implications to this idea, because what we're doing is we're bringing back the idea of teleology, providence, prophecy. The idea that a prophet can make predictions into the future doesn't seem so strange when we realize that the past came from the future, emanated from the future. And also the idea of synchronicity and law of attraction. Law of attraction is not New Age law of attraction. I want this, I want that, I want the perfect man, slimmer buttocks, Mercedes-Benz by tomorrow, or else, I'll find a new age guru. I mean, what law of attraction is, it's this. It's basically the universe needs certain things to happen, and it's set up to happen because it's set up to bring back the cosmic Christ. So it's purposeful. The universe needs certain things to happen. Now, if it's not about what you want from the universe. Law of attraction, if you align your will to the universe, then because what you're doing is what the universe needs, then you will find in what you are doing, the universe will conspire to help you to realize what you want to do. But what you want to do is actually what the universe needs anyway. It doesn't make sense, doesn't it? So mysterious things will happen. You will throw the dice and it will end up six, hundreds of times. And this is synchronicity. This is true synchronicity, not New Age synchronicity, okay? So, and this is why, because it's providence and it's teleology. Okay, so this is a kind of a view of the universe now, which we're going to add back to and actually integrate with our fractal universe. It's really a way of actually kind of fleshing out our kind of our sacred cosmology. Now, what we do now is just to show that basically, if that's the entire universe, that really corresponds, this diverging process, and that's becoming the body of God. Okay, so that's the cosmic Christ, universal Vishnu. These are the essential chakras or emanations of God, the essential power points of God. Then that diagram corresponds exactly with this emanating out to create the physical body, this emanating out to create this kind of one world order, human race global village. And back to here again, that's the same diagram basically. Big Bang becomes the cosmic Christ. You see, it's a fractal that I explained earlier. Now the trick now is to show that your life story. Okay, what we do in life, our dreams, aspirations, what I talked about earlier, because I've fractalized the homeostatic needs, our pleasures and desires, good and evil, pleasure and fear. Basically, I need to show now how does that correspond, not to brain space, but to mind space. And how it works is basically these main centers of kind of regions of the cosmic Christ correspond to our main homeostatic needs and our main desires and our main drives. So we talk about context of intent and context of motivation, and this is like space, but it's space happening in mind space. But the same process of emanating into reality and competing and combining representations and converging to realize our aims is actually mapped to the process of the universe. And a central region, which is very important, is sexual reproduction. And a lot of people's ambitions is based around this. So we are basically, instead of having this perfect lock for the entire universe, this kind of pattern which the universe converges to, we construct the lock of our lives. But what we're doing in our lives, we're trying to realize and find the key to fit that lock. So even though this is the image of the universe, we are enacting this image but imperfectly. And if we don't become the cosmic Christ, but we can aspire to a pattern of achievement and a pattern of attainment. And that's fitting the lock to the key, but it's a microcosmic representation of the universe. So in our lives, we are emanating behaviors, and an emanation of our behaviors is intersecting. So this backward tree emanating backwards is exactly that tree I showed you earlier of a Bayesian analysis backward chaining back to our primary rewards. And the forward intersection is all the things we need to realize the rewards and realize that our ultimate aims. Now, just the final section of the talk. Okay, what does it mean to perfect a score? To really to get a perfect score? Now, okay, this is really interesting because if that's the diagram, I won't go through it. It just means that there is a cosmic cycle. You have the slides after the talk. That's a human life cycle, but there's also what's called the myth cycle. And this idea that mythology is talking about a spiritual journey, it's allegory for the hero quest. It's basically the heroes trying to unify with the universe, Odysseus, etc., Luke Skywalker. It's allegory for something spiritual and transcendent. And also the idea that the myth process is also the same as the process, the journey of esoteric religion. So esoteric religion talks about this journey of union with God. Somehow, if you do certain things, you become one with the universe. Okay, just in a series of hugely ambitious, kind of aims, we're going to try and explain, using fractal brain theory and our mapping fractal brain theory to the universe, why people can become God now, just to top things up. So, okay, the idea that there are these kind of hidden mysteries in the world, that the central idea in religion is this idea that everyone's God. Now, what we have is basically this idea that somehow you're God, but it's hidden from us. So with exoteric religion and esoteric religion. And esoteric religion talks about this idea directly, that you are God, and also talks about methods to realize the state of being God, nirvana, kingdom of heaven, or whatever. And it's the path, it's the way. And we're trying to understand what is that path and what is that way. Now, it makes sense to talk about mythology and this esoteric path as one and the same, because, I mean, Joseph Campbell describes the paths of Buddha, Muhammad, and Jesus in terms of mythic terms. And also myths, like Bhagavad Gita is contained in the myth of the Mahabharata, and Odysseus is contained in the myth of the Iliad. So, as mystic manuals, there's a very tight relationship between myth and esoteric religion. Now, we've got fractal brain theory, but in a sense, religion is fractal. Because in the Vedas, Upanishads talks about as is the human body, as is the human body, so is the cosmic body. As is the human mind, so is the cosmic mind. As is the microcosm, so is the macrocosm. And as the atom, so is the universe. So the idea of fractal religion, okay, fractal Jesus, you think I'm kidding, don't you? Fractal Jesus. Somehow a person is Christ, that Christ is within us. But also in the Bible it describes society, the church, as the body of Christ. But also Christ is the all, the universe is also Christ, so fractal Jesus. Fractal myth. Myth is happening cosmogonic on a cosmic scale, but myth is also happening in society. Camelot and disarray, the Trojan War, the warring factions in the Mahabharata, but also the myth is happening in the mythic hero. And fractal, this idea in myth and religion, this idea of a cosmic battle between good and evil. But this cosmic battle is also fractal, because Zoroastrian scriptures talk about this fractal cosmic battle between good and evil happening on a cosmos. Or Mazad, Araman, Spencer Manu, Angra Manu, they fight eternally. But it stresses again and again in the Zoroastrian scriptures that the fractal cosmic battle is happening in our minds. And fractal jihad, that Muhammad said after the last battle to establish the early Muslim community, he said, "We return from the lesser jihad." We return from the lesser jihad to the greater jihad. And that's interpreted as the lesser jihad was the pitched battle with knives and spears and weapons on a pitched battlefield. And the greater jihad is to create a better society. Now, Muhammad also said the most excellent jihad is the perfection of character. So jihad happening within the person, within society, factions of society, between factions of society, but also the cosmic jihad, the kind of shaitan, the kind of cosmic shaitan. So, fractal cosmic battle, fractal religion, fractal myth. Now, if we have this kind of fractal cosmic battle, and we also have this kind of fractal light and dark in the brain, in our emotion centers, and throughout the fractal hierarchy, then we have this kind of dialectic that's cosmic and throughout the universe, and also this kind of evolutionary theory, which they say is also universal. Doesn't it make sense to reason that this jihad, this cosmic battle, this battle in mythology and religion is actually one and the same as the battle going on in our minds, fractally, at all levels of our brain, and also in evolution? So there's another huge integrating of ideas here to say that it's actually one and the same. And if we're looking at a cosmic fractal theory, that actually makes perfect sense to look in that way. Now, the idea that somehow if you win this cosmic battle, and what is the cosmic battle if not to defeat your fears and desires? And if we defeat our fears and desires, somehow that we attain this kind of state of being one with God, being one with the universe. Now, what does it mean to win the cosmic battle? In Buddhist iconography, Nirvana is guarded by two cherubs, angels, and they both hold a sword. One angel represents fear, the other represents desire. If any fear, any desire, you try to approach the gates, they'll cut you down. And also in Taoism, the idea, passage in the Tao Te Ching, which goes, ever desiring, we see only the manifestations, and free from desire, then we see the mystery, we see the Tao. Somehow, fear and desire is stopping us from seeing a higher reality. But then our brains are totally wired up for fear and desire. A hypothalamus, amygdala, and medial prefrontal cortex, fear and desire. Round and round we go in our little journey around samsara. Now, there's this idea, somehow, if you can win this battle, transcend this battle, and totally overcome one way or another fear and desire, then you attain this kind of state of perfection. And because we've seen the emotion centers, this homeostatic kind of struggle to balance the light and the dark in our minds, in terms of this lock and key language, and also a way of defining perfection, then there's a mapping between disperfection, which people generally don't achieve in life, with the state of being perfect. But there's one final thing missing. And that last final thing, even if you're totally happy, all your homeostatic needs met, perfect score, you've really made it in life, there's one thing missing, and that's not knowing who you are. Now, there's one idea which is from Buddhism and also Hinduism, but it generalizes to other religions as well. And it's this idea of a causal path, Sutrayana, and a resultant path, Tantrayana. It's this idea that religion generally is this idea of doing the right thing, thinking the right thing, and also feeling the right thing, right behaviour, right livelihood, all these kind of things you kind of a priest or you kind of like your mother tells you. And somehow if you do these things right, you set up the conditions for this kind of amazing reward. You don't know what it is. You're told that it's some place in the sky, after you die. You're given stories, you're given allegory, you're given parables. And somehow if you behave yourself, then you're going to attain this ultimate thing. You're not actually shown what it is. But this idea also corresponds with what's called Tantrayana, where you actually, or Tantra in Buddhism and Tibetan Buddhism, where you are told who you are. And basically then your thoughts and your actions and your feelings are directed directly to the knowledge of who you are. So knowing who you are to realize who you are. Now it generalizes to other religions because all the other religions have these hidden mysteries. The hidden teachings of Moses, Kabbalah, the hidden meanings of the Quran and sayings of Muhammad, the Batin, and the hidden teachings of Buddha, what we just talked about actually, Sutrayana versus Tantrayana, and then throughout all the world's religions. The basic idea is that all these inner mysteries really say the same thing, and really all these different mystical techniques really do the same thing. So Tantra is all about, New Age Tantra is basically about generally middle-aged couples trying to spark up their sex lives. It's a man wears a bindi, woman wears a bindi, maybe a bloke calls the lady Shakti and a lady calls the bloke Shiva, and they put on some gentle New Age music, and then they have sex. So, and then what Tantra really is, Tantra really is about total focus on God, and basically is about meditation becomes your entire life, and the meditation focus becomes God. So even though you're having sex and you're doing all the things, you're not actually thinking about sex. That's the thing. You're not supposed to think about it. You're supposed to think about God, and it's not easy. I can't do it, but But anyway, that's real Tantra. But what I'm saying, and also in Kabbalah, the idea that in all the Shema in the Bible, that's to love your God with all your heart, all your soul, all your strength, and in the Gospels with all your mind as well. That is Tantra. And in the Kabbalah traditions, basically, meditating on God constantly through song, dance, and sex, and basically, really, these mystical traditions and all around the world are really they converge and really identical. So you have Taoist Tantra as well. The idea is that basically you get a perfect score, but you only get the perfect score if you know who you are. So it's basically once you know who you are, Tantra is a fast path because you know the result. It's called the resultant path because you're basically working from where you are to the results. So what I'm saying is, once you can explain to people directly and fully in the last talk that they are God in a way that their rational mind can explain, then actually revive the ancient techniques in a modern language, a brain theory, then this is really the key to reviving completely these ancient mystical traditions for the 21st century. Not in a way that's counter to New Age kind of distortions, but in a way that's completely, complete and whole. Yeah, I mean, basically, just to finish off, I mean, what we have in this fractal brain theory, this sacred cosmology, and this revival of esoteric religion is a complete return of these kind of ancient mysteries for the 21st century and for 2012. So, I mean, it's a really good time to be bringing out these things in the literally the last days of the age, literally, as we approach 21st of December. And in these ideas, there's a huge the huge political implications to these ideas. What we have in this time reversal sacred cosmology, the complete revival of prophecies and apocalypticism and providence, and also the complete revival of esoteric religion, which I did more in the last talk, explain how everyone is God. It's the complete revival of esoteric religion and the apocalypse archetype for the 21st century, which I show in another talk is very conducive to starting certain sorts of social movement. Okay, and if that's not enough, we're basically unifying science, religion, and philosophy in a way that's a complete revival of ancient mystery religion for the 21st century. And on top of that, just having a fear of brain, mind, and consciousness has huge implications for mental health, for learning, for self-development. And to cap it all, we have the keys to artificial intelligence and the technological singularity. And really what's going to come about soon is this startup at the end of time. And all these things taken together, if that doesn't make a difference and change the world and do something starting now 2012, then I don't know what will. And anyway, I'll leave it there. I could go on for hours, and there's loads of talks coming in the pipeline, so I'll end it there. Thanks very much. Thank you very much for coming.